You are on the first shift, I think, for
Yes,
running.
we're
You as
both
well.
ignited.
Okay. Let's do it for now. Thank you. I'll find out how to get up there, and then we can let people know.
The posters can be put up right.
Yes, yes, yes. Thank you so much.
Test. There's got to be stairs.
Check 1, 2, 3. I've got a Camaro in my front yard. I've got 4-ball tires in the garage. Someday I'll get it on the track, and baby, when I do, there's no turning back. Dum 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 dum. Hast du was? Okay. Aber hast du Ton im Stream und alles auf die Presenter? Check 1, 2, 3, 4, 5, 6, 7, 8, 9. Mhm. Verstehe. After, yeah? Die ein, yeah, okay, good. Check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Caught in a trap, and I can't walk out. Because I love you too much, baby. Oh, we can't go on together with suspicious minds. Hi. Good morning. You're the first one speaking. Do you want to use your computer or this is this?
I'm going to try to use my computer.
Okay. Yeah, as far as I know.
HDMI. Hello, hello. Okay, we can start. 9 a.m. Thank you all for making it here. I hope you had a fun game last night, if you watched it. That's the only horse I know by name, and thank God it's Spanish. Okay, before I talk about some logistics, I wanted to just show you the SOC and the LOC. So I already want to thank all these people here for helping, setting the scope of the meeting, reading all the abstracts, and agreeing to running around all week and helping out. So the LOC has today, maybe tomorrow, I guess not for the full week, these t-shirts and a red lanyard. So that's how you can recognize us. Right, and some logistics now before I hand over to Matteo and Andrea to open us officially. So the program today and tomorrow will have mostly keynotes and then around 60 contributor talks. If you have a talk and you haven't done that yet, like before your session starts in the break, please come here and check that your laptop connects okay, because the idea is everybody brings their own laptop. It's HDMI, USB-C. We have about 50 posters, which will be shown all week over there in that room. We have a panel discussion on Friday, and we'll have long breaks. And the idea is, just time to chat, start collaborations, whatever you want to do. Lunch is on site, downstairs, and the conference dinner is also on site, I think, out in the garden if the weather is nice on Thursday. If you signed up for the conference dinner, there's like a rainbow-colored sticker on your name tag, and if you have an accompanying person, it's 2, like 2 on each side. Right, you already paid for dinner, but if you want to drink something, then you have to pay again, I'm sorry. So just want to get that out there. For the panel discussion on Friday, we'll do a Slido poll. We'll open that some point later this week to not have it overflow, I guess, where people can suggest and upvote questions that they want to ask the panel. There will be a kind of panel plenary mix. So I think panel discussing, some contributions from the audience. Okay, Wi-Fi, I think I've never scanned this QR code, but I think that should also do it. But so this is the Wi-Fi. If you have Eduroam, that works as well. If you haven't joined the Slack yet, you can do that. It's also in the email that I sent around. You can scan that code if you want to. And that's useful for announcements. If you have questions about the talk, about the posters, you want to contact the LOC. There should be like an LOC behind the names. I'll just leave that up for a second if people haven't joined yet, by just one person. Okay, before we start talking about the logos, this was our placeholder, which was good that it was a placeholder. It's partially inspired of having things which aren't copyright protected. This is what that leaves you with. But we had this amazing logo contest, so thank you very much to everybody who submitted a logo. It was a very tough choice. So in the end, Dario won the contest, so thank you. Yes, and I wasn't sure when looking at these if there's maybe an AI gradient. It's not gradient sorted here. But the SOC had fun picking the logo. And with that, speaking about logos, there's a great tradition for nice logos at horse conferences. This is the original Horse 1 logo. And this was pre-AI, right? So amazing. So with this, I want to hand over to Matteo and Andrea to talk about the scope of the original meeting, how it has changed, and what we'll expect to see this week. Thank you very much.
Thank you, Paul. Thank you, everybody. It's quite a bigger crowd compared to the first original meeting, and we have to say, in our defense, that this was all Andrea, so it was a 2-people effort, like making the logo and the program the first. There's quite a lot more organization this time, which is actually nice to see. And so with Andrea, we decided why not to go down memory lane a bit and basically recover the scientific rationale of the first one. You don't have to read it, but the only thing I want to tell you is like basically you could almost entirely copy-paste it onto the current one, which I don't know if it's a positive or negative thing, because this was 2018. Sure, COVID hit and everything, but there are a few differences that Andrea will talk about. But basically, you can already see that even at that time, our struggle was that we want to measure eventually biomarkers, but we cannot forget that there's two communities that go on the planetary side and the stellar side, and those two communities have to talk to each other. Because otherwise we're going to have effects that we don't properly take into account, and those could bias or otherwise hinder our ultimate goal. So without further, this Andrea will talk about. So Andrea, I'll hand it over to you for the more detailed differences.
Yeah, so hello everybody. So I'm very happy, like Matteo, to be here again. Very happy to see so many people increasing the number. Just one point, maybe you can say this. When I approached you in one conference 2015, that was nice because I really wanted to do a chance between planet and star. That was nice. I just came after your talk, and then we started to discuss, and we organized this conference. There are differences, I think, as Matteo said. There are advent of new instrument, the advent of JWST, of course, as well. New approach of analysis that you can read about for Bayesian retrievals on HiRISE. There is a whole new float of ground-based instruments that will come. And for concerning star, we have also large stellar surveys and new models, complex models that can actually go now and in the future to characterize better the star. But what is missing, at least to me, and what will come, one thing is, of course, the ELT and the new instruments to come. And this coupling between the two communities is still, and we see this in the next slide, between star and planet at high spectral resolution. We are going to be there, but we are not there yet. And the last point, that this time we talk about this, but instrumentation, so the coupling between imaging and high resolving power for spatially speaking. So I think I go on. I don't know, just a couple of...
No, we just compared also the map of the participants based on their affiliations, and also here there aren't many differences. I'm gonna flip back and forth. Don't worry about what the colors mean. They have been divided roughly in, obviously the number of people is higher for this conference, but there's only a very few new countries, but some of them, especially the UK and obviously Germany, have increased their presence in percentage for this one. If you want the numbers, we can obviously provide these. The last thing that is interesting and also quite not what the ideal situation is that even in this meeting, like the last meeting, there's a vast majority of planetary or exoplanetary talks. Stars and instrumentation, unfortunately, do not even make together half of the contributions. And this is somewhat expected given the hype, but again, like the meeting is just to reinstate that without the three communities working together, it's going to be very hard to do things, I wouldn't say properly, but as robustly as we need as we move into the next decade. Well, that's it for us. So I think Paul has invested us with the authority to officially declare open this two HoRSEs or HoRS2 meeting. And since I'm the chair of the first session, I'll just stay here and, for a little longer. So first up, we have the first keynote speaker, Jens Hoeijmakers. So I've had the responsibility to pronounce your name, Jens, and I hope I have gotten close enough to the actual pronunciation.
If you don't know worries, I've heard all sorts of things. Is it going to slide down? That would be a disaster.
I hope so. No, I hope not.
All right, so yeah, I would like to first of all thank the organizers very much for giving me this opportunity. I was present at the first HoRSE conference in 2018. This is something like 6 years ago. I have always looked back at this conference thinking that this was one of the conferences that I felt that we should have more of. So I was overjoyed to hear that we were going to do 2 HoRSEs, and I'm also very happy to kind of open this conference with this first talk. I was given the honor of trying to give you an overview of the field, as it was called. Paul sent me an email saying, could you give an overview of the field? I've got 25 minutes to do so, and that means that I will not be very successful at that. I'm going to try my best to cover as much as I can, but as you will see, it will actually be has to be quite narrow. Maybe the most useful thing I'm going to try to do is for everyone who's giving slides on cross-correlations, you will not need to show many cross-correlation time series and traces anymore, because at least I will take that away from you. Saves everyone a couple of slides down the line. All right, so I'm Jens Hoeijmakers. I am currently employed at Lund University. There I lead a small group where we do exoplanet atmospheres, mostly high-resolution spectroscopy, mostly ultra-hot Jupiters. This talk will not be about ultra-hot Jupiters as much as possible. Instead, I'm going to try to keep it more general for all of our benefits. What we are mainly trying to do when we do high-resolution spectroscopy, or perhaps any type of spectroscopy of our planet, is to try to characterize its atmosphere. And that means that we are after observable properties like temperatures, pressures, chemical compositions, or maybe chemical profiles, as well as atmospheric dynamics, and maybe differences between sides of the planet where the gas flows from one side to the next. These are the things we are trying to observe when we are doing spectroscopy, including high-resolution spectroscopy. Now, the type of science questions that we're trying to answer depends a little bit on the type of target that we're looking at. So for hot Jupiters, we are very interested, evidently, in the details of the compositions of their atmospheres, because we have this idea that their atmospheric composition may be representative of the bulk composition, and the bulk composition may carry memory from the formation history of our planet. When we are looking at high-resolution spectra, but also high-signal noise spectra that are now coming out of James Webb, we may have the ability to constrain atmospheric structure as well as see climate patterns from different sides of our planet. So when it comes to the hot Jupiters, we are very much into the details of how these planets work and where they came from. Now, with the coming of big new toys such as James Webb, we are starting to be able to access the atmospheres of smaller planets as well. So we are interested in understanding Neptune-sized planets, and it turns out that these planets may be very enigmatic. Classically, they have been perceived perhaps a little bit as mini versions of hot Jupiters, but it turns out that they have very unique compositions, formation pathways, atmospheres. And so we're really trying to piece together what are these atmospheres even of Neptune's and sub-Neptune-sized planets. There is interactions between the interior and the primordial hydrogen-dominated atmosphere that can create very interesting outcomes for the atmosphere. Now, high-resolution spectroscopy has, of course, mainly focused on hot Jupiters simply because of the fact that we are doing this from the ground. And mostly we have not been able to access smaller planets, but that is obviously going to change over the next few years. And finally, of course, we've got the rocky exoplanets, and there we are not asking, I suppose, very sophisticated or detailed questions. We're really mainly interested in whether or not these things have atmospheres at all, and whether we can observe them. Only after that, we will have the ability to start asking questions about what these atmospheres are, and whether or not there is any signs of life. So there is this sort of track that we are all on towards the smaller planets, but the science questions that we are able to address are going to be evolving in time as our instrumentation improves. Now, before I continue, I would first like to give you a small disclaimer. Because I've got a very small amount of time, I'm not going to be able to do most things that I might want to do. I'm not going to talk about reflected light, unfortunately. I cannot talk about directly imaged planets, even though there's a very interesting things that you can do with high-resolution spectroscopy or similar techniques on directly imaged planets. I cannot do single-line detections either, even though there's been very interesting things happening there as well. I cannot tell you what we're going to have to do with James Webb. I think there was going to be a lot of talks about retrievals, and I hope that James Webb is going to get its stage. It'll probably get plenty of attention. Sadly, I also have only one slide about stars. I'm sorry to not add to your pie chart, make that chunk any bigger. And I'll probably miss a lot of papers that have come out recently, so excuse me if I don't show your favorite topic or paper. Because what I want to actually focus on is, first of all, the application. How do we use high-resolution spectroscopy? Because I realize that maybe not all of you are actually very intimately aware with what we actually do. And if not someone is going to explain what these cross-correlation traces are like, you might not actually get this later on. That's the first part. And the second part, I'm going to focus a bit more about the science questions. I think the main scientific problems that we are having, that we are struggling with, that we are going to need to address. So we're starting off with our geometry. And as I said, we're not dealing with directly imaged planets. So this is the transiting geometry. And over the course of our orbit, our planet will transit and will also show its day side, which allows us to get a day side spectrum. Either way, the planet will produce some sort of spectrum that we can observe, and throughout this talk, I'm not going to distinguish much between transit and emission spectra. For my purposes and for the purposes of the data, they may be very similar, even though they're slightly different observables. So our planet is creating a spectrum, and this is a high-resolution spectrum coming out of the planet. What we see, whether or not we see it as a high-resolution spectrum, will depend on the instrument that we're going to use to actually observe this. But this is a model of a high-resolution spectrum that I made with petit ratrons to show you the richness that we're after when we are using these high-resolution spectrographs. And you have to zoom in very far in order to see any detail where these lines are resolved. And this is where we are doing our science when we're doing high-resolution spectroscopy. Now, these models are very high resolution, but depending on the instrument that we're using, the resolution might decrease by a certain amount. And with a high-resolution spectrograph, ideally, that is not very much. If you're going to do this with something like James Webb, which has significantly lower spectral resolution, these lines are still going to be there and they're going to be captured by the instrument. It's just that they're going to be smeared out by a much larger amount. I personally do not think that there is much difference between high and low resolution spectroscopy. Even though these communities have traditionally been quite far apart, the spectrum that underlies the problem is the same, and our analysis methods could be at least quite similar. Now, what is unique about high-resolution spectroscopy, at least our technique that we've been applying, is the fact that we can resolve velocities. So when our planet is orbiting the star, it is going to do so on a curved orbit, which means that its orbital velocity will be projected along the line of sight differently as a function of time. It will be seen to accelerate, and if the orbit is close enough, then that acceleration can be significant over the time span of a typical time series observation. And so it's this acceleration of the planet that we use in order to distinguish its faint signal from the much brighter host star. And this is one difference with space telescopes, because in space, with Hubble or James Webb, you don't really need to do this. You don't actually really need this, because you have absolute flux calibration allowing you to compare the in-transit over the out-of-transit spectrum, divide or subtract the two, and you see the difference, and that's your planet spectrum. From the ground, we do not have this ability, and therefore we need a different way of distinguishing star and planet, and that is what this acceleration is really important for. Because it's a feature that the planet displays that the star, with its overwhelming flux and spectral line, doesn't have. So we're taking time series spectra. This is often plotted in this two-dimensional frame where you have got wavelength versus orbital phase or time. And because our planet is accelerating and it's producing a spectrum during the transit, those lines are going to be shifting as a function of time, and that creates this very typical slanted appearance of these spectral lines. So over the course of your 3 or 2 or 4 hour transit, these lines will shift by a number of kilometers per second in velocity, and if your planet is very close in, that number could be quite large, could be tens of kilometers per second of acceleration, but if your planet is further away, that acceleration is going to decrease, and that's going to be a problem, as I'll show later. Now, this is a very clean model. This is just a transit spectrum model of a planet without anything else. In reality, we are, of course, looking at multiple components. We have the planet transiting in front of a star that has its own spectral lines, and we're looking through the Earth's atmosphere, which also has spectral lines. And so very often our planet lines are going to be slanted, but they're going to be hidden inside this much stronger barcode of a spectrum that the star and the Earth's atmosphere are creating. And so the game is to try to get rid of all of this extra signal in order to isolate this small planet contribution. Now, the main component that we use, of course, is this time coverage. We take a time average of our spectra. We subtract that out, or we divide that out of the data in order to try to recover our hidden planet spectrum. But the noise is now set by all those photons that were not from the planet, and so obviously this is going to be a very noisy measurement. In the case of James Webb observations, I've looked at some James Webb data, you can almost see this planetary spectrum in the raw data if you squint your eyes hard enough. From the ground, we're using telescopes that are as large, or sometimes even larger, but it's never like that because the Earth's atmosphere has modified the flux a lot. And also because our spectrograph is dispersing all of this light over way more pixels. And so even though we get the same number of photons, they're spread out over way more noisy pixels, so you will never actually able to see, or almost never you'll be able to see the spectral lines of your planet in data like this. And that's why we have to use tricks in order to average this data further, average all of these pixels further in order to obtain the flux of the planet back. And so the trick we use for that is cross-correlation, where you take your noisy data in which there is these embedded planet lines, they're hidden in the noise, and you take a template of those lines that you're trying to target, and you shift them over, you match them over each other, and at the right location for the right spectral lines, that is, for the right model that goes in, at the right rate of velocity, your planet is going to create that coherence addition of those spectral lines, making your planet appear in these cross-correlation functions. Now, because we're taking time series, of course, this is a two-dimensional plot again, so now we have transferred the wavelength axis into the radial velocity axis, and if there's plenty of lines, then you will see that your planet trace is going to come out in this time versus velocity space. Now, often, things are not so good, or at least they were not so good. I've got the feeling nowadays we're publishing a lot of papers where you can just see the traces of our planets very clearly, but this didn't used to be the case. So very often we will actually have to do another averaging, which is in the time dimension, where we're going to stack along this line in order to further beat down the noise. And that's how you end up with these KPV-cis diagrams that we always show. This slant is not necessarily known. It is proportional to the orbital velocity of the planet, and you may or may not know this. So we have this tradition of making these velocity diagrams where we do a velocity transformation, transforming the y-axis now to orbital velocity versus radial velocity, and that creates a blob at the correct combination of velocities where a planet lives. And so these are the plots that we've traditionally always made in order to visualize our signals. Now, these have always been very useful to detect species. We've been very interested in detecting molecule this or that, or atom this or that. But already in these diagrams, you can see that there's more going on with our planets. And one of the things is that we can access dynamics. If you think of your transiting planet as a rotating planet with an atmosphere on top that is swirling around, it has a velocity profile. And so all over your planetary terminator, there may be components from the spectrum being generated at different velocities. And that is going to modify the shape of your cross-correlation signature. And so already, almost 10 years ago, I think it is, we've been thinking about how we can use this technique to measure effective dynamics in the planets. And I've got here some recent examples where we do predictions with GCMs now in order to determine whether or not we can see effects that are in our GCM models back into our cross-correlation functions. Lisa Nortmann is going to talk, I think, right after me about a very interesting double trace that you're seeing in one of her planets, indicating that there is rotation and also clouds in a planet where this trace is really split up into two different parts. And besides seeing dynamics, we can also just do model comparison. So by injecting models into our data, even though these cross-correlation functions, they sound a bit scary and they're a little bit obscure sometimes what they mean. It also depends a bit on how you define mathematically what cross-correlation function you're using. But you can do model comparison and you can see whether or not your signal is strong or weak compared to the planet atmosphere that you might be expecting. Now, this is the state of the field in about, I would say, 2016, even though these KPV-cis diagrams and detecting species are still very useful and we still do it a lot. But what was recognized around 2016-17 was that we actually really would like to do model inference, like all the folks who are retrieving on HST and nowadays James Webb Spectra are doing. We would like to do model inference as well. And it was actually realized that this is not only possible, but actually the machinery that we have built through the cross-correlation function is quite similar to computing likelihood functions. So if you take this cross-correlation template with which you are moving over your spectra, and instead you replace that with a proper model of your atmosphere, almost the exact same mathematics leads you to computing a likelihood function, and that means that you can now do model inference, parameter inference. And this is really starting to gain traction, I've got the feeling, over the past few years, where different groups are now spreading out and almost publishing, I think monthly, we are seeing these retrievals now appearing on arXiv. And I think that's something that's been long awaited. Now, doing retrievals is of course very difficult, and I'm going to talk a bit more about model challenges in a minute. But what it turns out is that it works the best if you have ratios of elements that you would like to investigate. Whenever you do a lot of this data preparation that I have not really talked so much about, getting rid of tellurics, getting rid of the average spectrum, you may make errors and you may affect your model. When you're doing model inference, of course, those details are very, very important. But if you take ratios of elements, it may be that you're actually self-calibrating some of those errors back out and making a lot tighter constraints on the individual ratios rather than on the individual elements. So there's a couple of quite recent papers where I find that the uncertainties, where we see that the uncertainties are actually becoming quite small. Now, this mostly works the best for ultra-hot Jupiters, where you've got many species that you can take ratios of and many different lines that are all cleanly resolved without many tellurics that are in the optical. But we're starting to get sort of DEX-level uncertainties on elemental ratios these days, and I think that is very exciting. And this was not the case in the last conference, obviously. All right. Now, the second part is onto challenges. There's many challenges, I think, that we are going to have to overcome over the next few years. We're going to be presented with a lot of new toys, a lot of new instruments that are going to be able to image planets or reveal the spectra of planets at much greater detail than we have been able to do so before. But I think before we reach there, we need to solve a number of important problems. And these may actually have been, this slide may have actually been up in 2018 as well, because I don't think a lot of these things have changed that much either. The first of all is telluric lines, especially if you're working at infrared wavelengths. The telluric spectrum dominates, and the telluric spectrum is very time dependent. Since we are taking time series and time average of things, we want our spectra to be constant, but if you're looking through the Earth's atmosphere, they're not. Secondly, the star is a star, and it will behave like a star. And some stars are nicer than others. Some stars will really make it difficult to see your planet in front of them, and that is going to require a lot of additional understanding, I think. And finally, although I'm very excited about how we are able to retrieve parameters out of our planet's spectra, model complexity is going to have to increase in the near future. And so I'm very quickly going to go over this because most of you will probably be familiar with this. Telluric lines, there is essentially two flavors of two strategies to deal with it. Either you're trying to directly model the spectral lines. This works best if you're in the optical when there's not too many lines to model, I suppose. But especially if you go to the infrared where the telluric spectrum is really crowded, people often resort to blind detrending methods such as cis-REM in order to suppress the residuals. And then you have this very big question of what does that do to my model spectrum if I'm going to be doing model inference? How many cis-REM components do I need to remove? And there's many papers written about trying to optimize this problem. And this is not going to go away for the near future because the ELT will be equally hampered by telluric spectra as our VLT is. The second issue is stellar effects, and there is, I think, broadly two classes of issue. First of all is, I think, what we've come to know as the Doppler shadow, or rather, maybe more generally, disk inhomogeneities in the stellar spectrum that are more or less predictable, because the star is a rotating disk. Your planet is going to obscure part of that disk, and if the star and the planet have spectral features in common, this creates a time instability in the stellar spectrum that might actually mimic that of the planet. And so if your planet, if you're searching, for example, for CO lines, but there's also CO in the star because it's a late type star, or you're searching for sodium in your planet and this is a solar type star or even a hotter star, this is a problem that you're going to run into. And you're going to have to understand your stellar surface in order to correct for this, as well as your stellar spectrum, of course. Secondly, there is a class of inhomogeneities in the stellar spectrum that are maybe harder to predict. Spottiness in stars, but also pulsations in the hotter stars can make the stellar line profile very challenging. Anyone who's worked on WASP-33 will know that this is a plot of the WASP-33 star line after subtracting the average spectrum. You will know that it's very difficult to see any transit signatures of WASP-33b transiting in front, and you're almost immediately resorting to day-side spectra in order to just circumvent that. So modeling stellar pulsations, but also I think this is a very important issue when it comes to the M-dwarf stars, because M-dwarf stars are spotty. Spots are rich in what they call dust or molecules, and those are maybe exactly the molecules, CO, water, perhaps other things, that are in our transiting spectra. And now we're talking about transiting planets that are much smaller than hot Jupiters. So our signals are hard to tease out of these M-dwarf spectra, even if they were not spotty, even if they were not irregular. And so the M-dwarfs are going to present a very big problem. And everyone who's working on TRAPPIST-1 with James Webb will already have seen this, that it's very difficult for James Webb as well to pull out spectra that are actually of the planet and not of the star. So stars are a big deal, and this is not going to go away no matter how big our telescopes are. Finally, an issue about model complexity. Here is my layman's attempt at making a model spectrum. I've used petite retrans of Paul Mollière to make a very small model of a transmission spectrum. And this is what we call a one-dimensional spectrum, a 1D spectrum, where the atmosphere has a profile, a temperature-pressure profile, that you can choose, or you can maybe calculate or expect what it is. And then you couple that with a chemistry model too. So in order to get a spectrum, you need to assume or calculate your temperatures and then calculate in some way the chemistry, and then out comes your spectrum once you have a big library of opacities that link this chemical composition to spectroscopic activity. Well, this is the example of the transit model. If you go to emission, the spectrum actually becomes very sensitive to the temperature pressure profile. If you are an inverted profile, you will see emission lines. If you are non-inverted, you'll see absorption lines. So especially day-side spectra are useful for trying to constrain the temperature profile. And again, you'll have to put in opacities and you'll have to put in chemistry. Now, when we're doing retrievals, this is already fairly difficult. Any one of you who has done retrievals know that these retrievals typically don't take a day or a few days even. I know examples where it even takes weeks to back out the chemical abundances that went into the 1D model that we fit to our spectra. Of course, I don't need to tell anyone that planets in reality are three-dimensional objects, and there is no temperature profile. There's perhaps a range of temperature profiles, both from the day side to the night side, where one side is hot and the other is cold, or around your terminator, which we always assume to be a sort of homogeneous donut. Not always. There's people who are now trying to make progress in this. I think Sid is going to probably talk about this in a little bit more detail. Where we're going to have to deal with the fact that the temperatures are actually not constant at all. And the average spectrum that you get out may not be the average of any of these temperature profiles that you have there. And there's no easy way to generalize a one-dimensional spectrum into 3 dimensions and still be able to back out single numbers, which is what we ultimately want to do. Single numbers being, for example, the carbon-to-oxygen ratio or the metallicity of our planet. Now, hopefully, the atmosphere traces the bulk values, hopefully. But right now, when we're taking measurements, we're sticking thermometers and measuring sticks into our planets from various sides, we're not even sure that we are measuring representative properties of the entire atmosphere. And this is something that we're going to have to deal with as we're going to see more detail of our planets. This is a plot that is, or variations of this plot are very typically made, showing how, and especially in the case of ultra-hot Jupiters, we are already really sensitive to this. Ultra-hot Jupiters rotate during their transit, and therefore they scan across the terminator region, and we can actually observe in our spectra some of this variability that's taking place in the spectrum as a function of, as a result of this rotation. And of course, this is on the map, and people are trying to deal with this, make models to make progress. And this is mainly in the community of people who make GCMs. So we can predict what the 3-dimensional structure of our planets are. A lot of physics goes in there, and they're very slow to run. So when we're in the business of doing model inference, we're not very close at being able to use GCMs in order to back out our elemental ratios. And this is a problem that I don't think will go away. But we'll need to do so because already for now 4 years, we've been actually seeing this 3-dimensional structure in our planet atmospheres via these slants and kinks in the traces. All right, very quickly about the future. Many of your talks in this week are going to be about the future in one way or the other. I've seen the program and there's very exciting titles. It's clear that in the future we are going to have very, very nice instruments, big telescopes in space, high resolution spectrographs, 30-meter class telescopes. Yesterday I went to the webcam of ESO and I looked up what the ELT looks like these days, and it actually looks like a telescope now. By the time we have the next HoRSE conference, hopefully not 6 years in the future, but maybe 6 years in the future, then we might already be playing with our first ELT data. And the problems that I think we're facing are mostly of a theoretical, but also of a data analysis nature. They are not going to go away by themselves. And so by the time we switch on these very big telescopes and very interesting, useful spectrographs, Ariel is going to come online, James Webb database will be overflowing with data. We're going to have the same problems to solve. These problems were already recognized, I think, most of these during the last HoRSE meeting. I have the feeling that since then, my list of worries has actually grown. So I've done a lot of work over the past few years. I've become more worried about some of these things. And like Matteo, I don't know whether that's a good thing or a bad thing, but it's very clear that we have a lot of work to do. I'll very quickly skip this. I made a small simulation of the things that Andes will be able to see. Andes will be able to resolve individual spectral lines in hot Jupiters. We will no longer need to do cross correlations anymore. So any one of you is daunted by the cross correlation function, didn't really want to get into it, well, you can just wait for a few more years, and we're probably going to just step away from that because we're going to do single line spectroscopy soon. With Andes, we'll also be able to access small planets. This is a cross correlation trace predicted for K2-18b. The issue is that it's not slanted anymore because this planet does not have a lot of acceleration. And I wonder if that is not a very, very big problem that might actually limit our ability to use this technique at all. So the key outstanding questions that I'm going to leave you with, and this is just a subset, I'm sure there's going to be other big important issues, but this is the stuff that keeps me awake at night. How can we actually make planets 3D to be able to do model inference? To the GCM people, this question translates to, how can we make GCMs fast? And have you included chemistry models that are not equilibrium chemistry? Right now we are in the business of when we do chemistry, we often apply equilibrium chemistry down to hundreds of Kelvin planets, and that's probably not okay. How do we include dynamics, condensation, photochemistry, and keep things fast so that we can still do model inference? Can we live without a significant acceleration? Is this method actually going to break? Is ground-based spectroscopy going to break for planets that no longer accelerate? Finally, M-dwarfs. I've not shown you many examples, but M-dwarfs can really mess with your spectra, both in space as well as on the ground, and this needs a lot of attention. And finally, line lists. A lot in the first HoRSE conference was about line lists. We were very worried about it. I've not seen so many talks about line lists, and I hope that's good news. But I think that there is still a lot of work to be done. There was a new VO line list that was published, or it's not even published yet, I think. It's ready, though, and I know some people who are playing with it. Apparently, the line list itself weighs 1 terabyte, and it takes a while to transfer it to your server where you're going to do opacity calculations. I think I'll be happy if I have a VO spectrum in a few months. So the magnitude of our data and the input data as well is not shrinking either as we are building our bigger telescopes. So these are the questions I would like you to ponder during the week and discuss with you. I'm looking forward to all of your talks. I thank you very much for your attention. The final thing I want to say is that I have not stuck to the theme of HoRSEs. I have not put any HoRSEs on my slide. I didn't have the idea that I could compete with all of the memes that are about to come, probably. So the only thing I've done is that I've put a picture of my little baby sitting on a horse. Thank you.
Is there any question? Breaking the ice is... I'm going to ask the first one, then anticipated, and he's stolen your scene for a while. Lisa, do you want 5 minutes? 3 minutes? 3 minutes, 5 minutes warning?
Oh yeah, thank you. 3 minutes, I guess. But no, make it 5. All right. Also, I can see the clock. So, hi. I'm very happy to be. I was in the first HoRSE conference, and I also remembered it as one of the best conferences I've been to. So I'm very happy to be back. And today I get to talk about some results that came out of CRIRES. I'm part of the CRIRES consortium, so this is part of the GTO observations. I have put a list of the people who are working in the planet team, so the team that is focusing within the consortium on the exoplanet atmospheres work, exoplanet atmospheres science case. Can you see my mouse? Yeah. You can see that we have observed a sample of planets that are ranging from ultra-hot Jupiters to actually down to cooler rocky planets. And we are observing them both in transmission as well as in emission, and really sampling all kinds of different science cases within this group. Highlighted in black and boldface are people of the consortium who are also present in this conference. So today I will especially focus on the planet WASP-127, which we have observed in transmission. This planet has roughly a Jupiter radius, but a much smaller mass, so it is a very puffy planet. It is not an ultra-hot Jupiter. It's 1,400 Kelvin, at least in the equilibrium temperature measured in the day side, and it's on a about 4-day orbit. It has been observed from the ground. First observations were done in the Canaries with low-resolution ground-based instruments, like the Grand Tucan. And then later, Hubble Space Telescope observed that, and of course you can see here that the scatter is much reduced. But the general picture that you can see in the low-resolution spectrum is that it seems to be feature-rich. You can see clearly the water absorption, and there might be some sort of absorption and haze that still obscures part of the atmospheric features. And the most comprehensive study in low resolution that had been done was by Jessica Spark. But since you are measuring only up to here and you don't really cover the carbon bearing species like CO2 and CO, other than with these 2 Spitzer points that we had pre-James W, you have some struggles to constrain the C/O ratio of these planets that Jens has pointed out is one of the interesting parameters that we would like to get out of analyzing the atmosphere. And so depending on what assumptions are made in the retrieval, you might get a quite high C/O ratio of 0.8, or you might get a spectacularly low C/O ratio of around 0. Further high-resolution studies that came afterwards were not able to reproduce these strong signals in the visible, which was kind of surprising. So we decided to observe this planet in the K-band, which is roughly around here. And what we would expect from CRIRES observations in the K-band is that we can at least observe water, CO2, and it is probing the region where methane and CO2 are having absorption features. What you see here are theoretical models. Here the assumption is a solar C/O ratio and metallicity. And what you see is that these features, these molecules have features in this wavelength range, but once you start including clouds compatible to what the low resolution spectroscopy has seen in the retrievals, you might lose quite a substantial amount of the signals of the methane and the CO2. Another factor that Jens just mentioned in the end is that if you have, for example, very strong water absorption, other trace species, such as methane and CO2 in this case, might actually be hidden below the continuum of the water. So you don't even need clouds to hide them. So this all is based on the assumption that the entire atmosphere is one homogeneous atmosphere, and you get one single spectrum from it. We have now already in the past seen people who have detected trace species that they might not have expected to see while there was also water in the atmosphere. And the explanation for that might be that you have these signals coming from a different part in the atmosphere where maybe water is not as strong. And as Jens mentioned, that we have, as a community, started to going forward to actually being able to resolve different parts of the terminator using the velocity velocity and time resolved spectroscopy. So the method that has been used in the past was mostly based on the fact that these ultra-hot Jupiters, which have very close in orbits, so 1-2 day orbits, are so close to the planet that during their transit, their orbit changes so much that the angle under which we are seeing them changes. So you are observing actually a different part of the terminator during ingress than you are observing during egress. This works very well for the close in hot Jupiters, but when you're starting to go further out, like for WASP 127, which has a 4-day orbit, you might be able to see here that the face that is covered during transit is much smaller. So the effect of angle change will be much smaller. So you might expect that we will not be able to do these studies when you're going to planets that are more further out. Despite this fear, we actually have been able to observe features that are off from the norm of the 1D expectation. And Jens already has given a teaser. So instead of seeing the cross-correlation in time showing a trace at the planet velocity, we see 2 traces, and they are offset by plus and minus 8 kilometers from the planet rest frame. They're moving exactly with the expected planet velocity. So if we are doing this KP-V-cis diagram, the peak happen at the expected KP, so at the orbital parameters that we are expecting for this planet. And if we are summing up all the signals in that, on that KP trace, we are getting this clearly 2 peaked signals. We do detect this double peaked signal in water and in CO. We also checked for methane and CO2, as I mentioned, and we do not see any signals there, which is in line with expectations, as I showed before. So how exactly do we get this 2 peak profile? Jens already mentioned that when the planet is rotating, we are starting to get a double peaked velocity distribution. For this planet, since it is on a 4-day orbit, these 2 peaks are still so close together that at instrument resolution, which in our case was 140,000, slightly higher than what we would expect from CRIRES, which is 100,000, these 2 peaks would still be unresolved. So this is under the assumption that the planet is rotating as tidally locked, and basically the planet is rotating once every orbit it does around the host star. If you're starting to spin up the planet more and more, you are starting to get these 2 peaks separated. And in instrument resolution, you will see actually 2 peaks. However, you will have a plateau in the middle. Now, we know from our solar system that we might have actually bands of winds rotating faster. And so if we are imagining that the fast velocity actually occurs in a jet around the equator, and the rest of the planets, so closer towards the poles, is actually rotating at tidally locked rotation, you might get a slightly different velocity profile with 2 peaks left and right and a signal in the middle. The exact shape of this signal depends on the width of the equatorial region. So if you make it wider, the peak in the middle gets smaller, and so on. Now, we don't detect either of these cases. We don't detect a plateau in the middle, and we don't detect a 3rd peak in the middle. So the logical assumption must be that the signals that come from that region of the planet might be severely muted. And so here's a scenario where we suppress the signal at the poles by injecting a model, by basically assuming a model that has no features, either due to high clouds or to very low temperatures that has features below the noise level. And so this seems to recreate a double-peaked signal. We are using this assumption now and doing a retrieval on the 2 peaks that we are detecting in the spectrum. So Here, just briefly mentioning that we are basically doing a log likelihood optimization. We are using Petit-Rattan's models. We are assigning each of these regions a different model. As Jens mentioned, we are not there yet where we can do retrieval with full 3D models, so we have to use a mock models with a lower complexity. And we do pre-processing of the models using the same steps that we do in the pre-processing of the data, although we are using the shortcut proposed by Gibson et al. I am getting to the results because I'm running out of time. So we find that the C/O ratio that we retrieve for this planet is actually quite close to solar and also quite close to the stellar C/O. This is in disagreement with both of the results that were were retrieved only from low-resolution spectroscopy, and apparently also in conflict with another high-resolution spectroscopy result that came out while we were working on this, which was done by the people working with Spirou, who did detect water but did not detect CO, despite the fact that they were looking at a very similar wavelength range. And due to the lack of CO detection, they also had a very low C/O assumption. We can also retrieve the width of the equatorial region and the maximum speed at the equator, which is nearly 10 kilometers per second, which is even in these temperatures supersonic speed, which is quite interesting. I'm also actually impressed by the width of the region that we retrieve. What we cannot constrain is the velocity at the poles, because we simply don't have a signal, so we can't distinguish between the case where we have cool temperatures or high cloud deck, and so we just know we have a very muted spectrum. Here I show the temperatures and cloud deck heights that we retrieve, and we see that they do fall into different regions, but within the 2 sigma levels they do still overlap. So despite the really nice results, it is still quite difficult to clearly distinguish the different areas in temperature. But you can see that the distributions, the temperature distributions between the poles and the hottest part of the planet, so the blue shifted part that comes from the day side to the night side, are clearly distinct distributions. So what's the implication? Well, first of all, we are moving towards being able to resolve 3D structure, but we also have to consider this structure when looking at low-resolution results and any results, because as I mentioned before, in the visible, features of this planet had been detected as muted. And if we consider that maybe we are looking at a scenario like this, then we have to realize that the signals that we expect at high resolution actually might be small in amplitude and split over different peaks. So we might want to go back and see if that changes the interpretation of these signals. I just wanted to have a brief shout out to there are going to be more talks of the CRIRES group later this week, but there are also results of people who haven't been able to make it here. And I just wanted to mention that we are looking also extensively in emission, and we have observed a large part of the phase of an ultra-hot Jupiter, where when you align to planet rest frame, also here you see some deviations from the expected velocity, which are somewhat in line with the fact that you're seeing a very highly irradiated day side that is rotating in and out of view. And since last time I was at HoRSE, I had the pleasure of talking about helium. Wanted to just say that we are still very interested in helium, and we're also following it up with CRIRES, and we have a result for an ultra-hot Jupiter, which will hopefully appear soon. Thank you all for your attention.
Thank you, Lisa. There is time for one question.
All right, welcome back, everyone. I'm Megan Bedell. It's my pleasure to introduce our speakers for this session, beginning with our keynote speaker, Elisa Delgado-Mena, who's going to be telling us about stellar chemical abundances.
Okay. Thank you, Megan. Can you hear me well? Yes, maybe I should get closer here. Okay. So first of all, I would like to thank the organizers for inviting me to giving this talk, which is going to be about stellar chemical abundances. So first, oh, sorry. Okay. So first I'm going to talk a bit about why stellar abundances are important, especially in what concerns the derivation of them with high-resolution spectroscopy. Later I will give some practical examples of how we derive these abundances, how we get them. Then I will mention some more specific results on FGK stars and how they have helped to establish the star-planet connection. And finally, I will briefly review some of the most recent results on M-dwarfs, spectroscopy of M-dwarfs. Okay, so why do we care about the stellar abundances? Why are they important? Well, the first thing we can think of is because planets and stars are formed in the same disk. Then they are formed from the same material. We can think that there should be a connection between them, right? We should extract information on the planets from the composition of their stars. And this was soon seen after the first discoveries of exoplanets back in the 2000s with still very small samples of stars. It was soon seen that there was a correlation between the metallicity of the stars and the presence of giant planets. At the beginning, it was not clear if this could be done by contamination of the stars by the planet material itself, but later it was seen with larger samples that this has a primordial origin. That is, you need to have a high metal content in the disk in order to form giant planets. As the techniques to detect planets improve and we could find smaller and less massive planets, we could also evaluate if this planet metallicity correlation holds for lower mass planets. And several teams found that this correlation is not so important. So the distribution of metallicities for stars hosting small planets, it was more similar to the distribution of stars, for example, these two distributions here, of stars in the field, or this example by Buhave and Latham in 2015. Okay, so now that we know about the planet metallicity, what about other elements? Because the iron is one of the most easy elements to derive. But what about other abundances? Can we get to know more also about the possible differences between stars with and without planets? So initially, the first studies, they were based in small samples. One important problem they had is that the comparison samples of stars without planets were not good enough because they hadn't been searched for planets, so it was difficult to compare. And also initially they were comparing the absolute abundances, but not taking into account the galactic chemical evolution, so not comparing stars at the same metallicity. However, in 2012, this work by Vigan et al. Found a clear and significant enhancement of alpha elements for stars at lower metallicity. So the blue and the red points are stars. The blue are stars hosting Neptunians, and the red are stars hosting giant planets. And it was clearly seen that the abundances of alpha elements, which is titanium, magnesium, and silicon in this case, it's higher. And this is probably telling us that these elements are important to form planets when the amount of iron is low. By having the chemical abundances of the stars, we can extract information on the bulk composition of terrestrial planets. And this can help us also to break the analysis between the density and the composition of the planets by applying these abundance ratios to the models of internal structure composition. Indeed, one of the first, if not the first, work by Bond et al. In 2010 that was combining both dynamical and chemical embodied simulations of planetary embryos by using as an input the abundances of the stars hosting planets, and they were able to determine these bulk compositions of planets, of these planetary embryos at different distances from the star, and then they could find that you can have a large variety of extrasolar planets formed in different distances from the star, depending on the abundances of the star, of course. And also the work by Seeger and Kuchner show how important are the carbon-oxygen and magnesium-silicon ratios. But okay, so the abundances can serve not only to better know your planet itself and the internal composition of these planets, but also to understand the environment in which the planets are formed, because we also want to know where in the galaxy these planets are formed. The age is very important also when you want to study the evolution. So for example, by using chemical abundances, you can constrain whether a planet was formed in the thin or in the thick disk, just by looking the alpha abundances. These stars here that have higher abundance ratios are the thick disk stars that are older, as you can see from the age. And this is the thin disk. And also by combining certain abundance ratios, the alpha elements, together with the S process elements that are forming other kind of stars, we can also get more information on the age. Because we know that the alpha elements are forming massive stars, and then these elements are released into the galaxy earlier, at earlier times. However, the S process elements are formed in less massive stars. In AGD stars, they are released in the galaxy later, in later times. By combining the abundance of different chemical ratios that we know that have this constraint with age, we can get estimates on the stellar age. And we can compare it to ages obtained from other methods like isochrones or gyrochronology. For example, you can see here the relations of age, of abundance ratios with age that also depend on metallicity, or here the plots I saw before. So by having the abundances, we can also have an idea of the age of our stars. Okay, so after these few examples of how stellar abundances can be important, I will show you here some very few examples of how we can get the abundances and how the methods work. So the basic ingredients you know to derive stellar abundances is, of course, stellar spectra. The highest resolution, the higher resolution you have, the better, because you will be able to disentangle more lines, especially those that are weaker. And of course, you need high signal to noise. Then you need a model atmosphere of your star, where you characterize the different shells of this atmosphere. You can use, there are different kinds of models in the literature, Atlas, Marx, Phoenix. You can choose from different kinds of models. You need a line list, this is very important, with accurate atomic data of your atomic and molecular lines in order to measure the abundances. And finally, you need a radiative transfer code, like MOOC, Turbo Spectrum, Phoenix, Inte, etc. And what are the classic methods to derive abundances directly from the spectra by looking at the spectra? So we have the equivalent width method that is based on the curve of growth. So we can obtain the abundances from the equivalent widths, direct equivalent widths of the lines, or we have the spectral synthesis. So in the first method, what we have to do is to measure the equivalent widths by fitting Gaussians to weak lines, so not the strong lines, okay? Because this direct correlation between equivalent width and abundances has to be done for these weak lines. So here I'm showing some plots of a code that I regularly use, which is the RS2 code. For example, these are two carbon atomic lines in the optical spectra of a solar type star. These lines are not very strong, but are good enough to be measured. So this is 30 and 19 milliangstrom. They can be well deblended, not for vehicular stars, but okay. These are two very well-used carbon atomic lines. Then you have other elements like yttrium that maybe you have heard about because it's useful to determine ages. For example, this element has a stronger lines. Sometimes they are blended, but we can deblend them very well. However, if you have fast rotators, for example, or you have lower resolution spectra, this is a HoRSE spectra. If you go to resolutions below 30 or 40,000, then this line will be blended, and then you will not be able to apply this method. Ah, okay, sorry. Okay. Okay, now? It works?
Now, yeah.
Yes? Okay, yes. Okay, and here I saw barium, which is another element that now became fancy because it showed up in the atmosphere of some exoplanets. And indeed, someone asked me if this line we can measure it well, so the answer is yes. these elements have very strong lines, which are easily measured just with equivalent widths, but you have to be careful because the lines are affected by hyperfine splitting, which means that what you are seeing here is not a single line, it's a lot of individual components. Then the other method that we can use is the spectral synthesis. In this case, what you have to do is to model the full spectrum in small regions and compare to your observed spectrum. This has to be used for elements in which the lines are blended. For example, this is sulfur, which has two components here, and you cannot disentangle it automatically with equivalent weights. And also, for example, for the case of lithium, which is a doublet, and the line is not symmetric, the higher the resolution, the more separated these components will be, and then you need to also apply a spectral synthesis to derive the abundances. Now I will mention one specific element, which is very important for people working in atmospheres, which is the oxygen. This element is quite hard to get in solar-type stars and cool stars, because the lines are very weak. Well, there is one line that is very strong, which is the oxygen triplet. However, it's in the red part of the spectra, so many of the spectra that we use don't have this region. And also this line is affected, is strongly affected by NLT, by non-local thermodynamic equilibrium effects. So you have to consider this, this effect at the time of deriving abundances. For the case of using these other two lines, which are the two lines that I have worked most with, this is the most used line, I would say. The problem of this line is that it's weak and it's blended with a nickel and also other smaller blends. Here I saw an example, a very high resolution, you see 650, of a G2 type star, so it's a solar type star, solar twin, let's say. And this is the line, so you see it's very weak compared to others. And it looks like normal, right? You can see, you can measure here the equivalent width or do a spectral synthesis, but in reality, this line can be contaminated. So here I saw an individual spectra of this star, because this is composed by 78 individual spectra, okay? It's a combined spectrum. So the individual spectrum look like this orange one that is normal, just, of course, it's more noisy. However, when you check the other spectrum, individual spectrum, you can see these lines here, which is an oxygen air glow, is produced by the Earth atmosphere, and you have to remove this spectra before making your combined template, because it can affect the line. For example, if you have very strong emission, it will make the oxygen line weaker, and you will have lower abundances, which can also have implications for the CO radius, for example. So you have to remove this spectra before deriving the abundance. Also, this line, the same line I mentioned, also it can have, if you see some kind of asymmetric, the black is the original one. This is caused by telluric absorption that can also make your line deeper than it is in reality, and then you also have to correct it. So sometimes this is easy to see because the line is asymmetric and you realize that there is some problem, but other times it's not as clear. And this is the other oxygen line that I mentioned before that we have checked in our works that gives more precise results. The problem is that it's super weak. Here I saw a K0 star, this is an F7, and this is a G2. However, so since the signal to noise of this spectra is not as good as the others, we cannot measure the line here. And these other cases are at the borderline of being measured. So you need very, very high resolution, high signal to noise spectra to measure this oxygen line. Okay, so now that we know more or less how to derive abundances, what have been the results for FGK stars? So as you have seen, we know quite well the spectra of FGK stars, and there are a lot of results in the literature, and these results have helped establish the star-planet connection, not only in metallicity, but in other elements, as I mentioned before. Here I saw the same work I mentioned before about Adivekian et al. In 2012 that used the HARP CTO sample that is composed by more than 1,000 stars. And here it was shown not only the alpha elements, there are other elements also that, like aluminium, that also show higher abundances at lower metallicities for the planet hosts. We have also checked that in this work for other elements, where we also find enhancement of abundances for these stars, but not always this is related to planet formation, it's just a consequence of galactic chemical evolution, because different elements are formed in the same way. And then we can see these trends. We have also checked for carbon, which is easier to measure than oxygen, as I mentioned before. We have also found hints that as you move to lower metallicities, you can have, it seems that planets, stars hosting planets, the blue ones, especially the small ones, have higher abundances of carbon, but the number of stars is much reduced, so this has to be checked with a larger sample of stars. But we have even observed that by considering stars only in the thick disk, also still the abundances of carbon is higher for stars hosting planets. So what this is telling us is that when you are at low metallicity, since you have a lower amount of iron, you have to compensate it with other elements that are important for planet formation, which means that probably at lower metallicities, you can only form planets in the thick disk, or it's much easier to find planets in the thick disk. And whenever you want to do this kind of population studies, comparing the abundances of stars with and without planets, you also have to take into account the galactic context. So where do these stars were formed? To disentangle the pure effects due to planet formation. So these abundances can serve to do these population studies, so just comparing stars with and without planets, but also for specific stars having planets, we can obtain the mineralogical ratios. So these are very important ratios to understand the bulk composition of exoplanets. So for example, the carbon-oxygen ratio, it controls the distribution of silicon among carbides and oxides. And also with the magnesium silicon, we can get to know how this silicon is distributed among the different silicates. So whether we are going to have planets with a higher content of pyroxene or a higher content of olivine, these planetary building blocks. Indeed, I want to make a stop here just for a word of caution about these abundance ratios, because these values that I'm showing here are absolute ratios, okay? They are not referred to the sun, okay? These are the absolute ratios. And depending which lines you use to measure these abundances in your star, you can obtain very different results or quite different results. So if you want to compare the abundance ratio in your star with that of your planet to understand the atmosphere of your planet, to understand if there are any differences, you have to be very careful on which stellar abundances you use. So here there are these two plots is the CO ratio as a function of metallicity done with the oxygen line at 6,300, which is the line I told you that can be contaminated by an air glow. And this is with the other weak line that we were able to measure it in the HARP sample, but in a lower number of stars because you need very high signal to noise. So the first thing we see is that this line has a dependence with temperature, and you can have higher CO ratios as the temperature increases. The green points, you see that they are move upwards with respect to the others. This is not seen here, where all the points are more or less mixed. This trend with metallicity, this is normal due to galactic chemical evolution. But not only that, depending on which stellar models you use, I did here a comparison between Atlas and Mraz, there can be very big differences, especially for cool stars, up to 0.18, which then translates into the absolute, into the comparison that you want to make with your exoplanet. So my advice here is that instead of doing the absolute abundances, you have to do the same analysis for a solar spectrum that you analyze in the same way as your star to calculate the CO ratios with respect to the sun, to your solar spectrum, and then to this value you transform it into the absolute CO ratio using the reference values in the literature you want, because these horizontal lines are the CO ratios that you obtain for the sun depending on which lines you use and depending on which models and depending on which atomic data you use for your lines, okay? So it's good to do this differential analysis to get rid of these systematics or at least reduce them as much as possible. And not only we can study the exoplanets, the abundances of the planet host from an individual point of view, but also to understand how these planetary building blocks distribute in the galaxy depending on which population they belong to. For example, in this work by Santos et al. In 2017, by using a very simple stoichiometric model using the abundances of the stars, the iron, magnesium, silicon, carbon, and oxygen, they could derive the core mass fractions and the water mass fractions. And it was seen that, for example, the stars that are in the thin disk have higher core mass fraction, meanwhile the stars that are in the thick disk would have planetary building blocks with higher water mass fractions. In a later study with more complex stoichiometric relations, Beach and Battistini that were differentiating these planetary building blocks inside and outside the ice line. They also show that, for example, when you are outside the ice line, this water mass fraction decreases with metallicity. And then it will mean that then you will have less water available for planets in these kind of stars as compared to the stars that are at lower metallicities. I also recommend to have a look at these newer papers on this topic because it's very interesting, but I don't have time now to talk more about this. Okay, and finally to end, the M dwarfs. Well, for the FGK, we have a lot done. We know these stars quite well. I think we can trust the abundances of FGK stars. Of course, you have to take care of these systematics that I mentioned, but we are quite confident about the results. This is not the case for the M dwarfs, where we are still, let's say, in earlier years of analyzing these stars. So, first of all, you cannot use optical spectra to derive abundances of M dwarfs because the spectra is very crowded. It's full of molecules. The continuum is blended, and you cannot do anything with that for a specific abundances individual. Of course, you can measure parameters. So then the studies have moved to the near infrared, where the continuum is cleaner. You can see here this work by Onegag using CRIRES spectrum. So you can measure individual lines to determine stellar parameters. But also even in the near infrared, you have to be careful with some molecules. For example, this is the H band with apogee spectra. And as you move to cooler temperatures, as you go down, there are water bands here very strong that depress your continuum. So this is a problem because then you don't know very well where to put your pseudo-continuum. And since to analyze the spectra, you have to first normalize it, it's hard to know where to put it because it depends on the temperature of the star. But you also need to know the continuum placement to calculate the temperature of the star. So it's a tricky thing to get rid of. Indeed, there are several works in the literature trying to derive stellar parameters, and for the temperature, I think the things go quite well. This is the work by Vera Passeyer et al. In 2022, where a team of different people using different techniques with the same Carmen's spectra derive parameters for a number of stars. So for the temperature, the different points agree more or less well. Of course, there are some outliers, but the methods work better. However, for metallicity, the discrepancies are very high, up to 0.2, 0.3 dexes in some cases. So it's still very hard to get metallicities for Ms. I think that now that we are having new high-resolution spectrographs in the near-infrared, like Carmen's, Spiru, NIRPS, CRIRES+, we will start to see more and more results, as I will show now. For example, this work by Ishiwaka, using Carmen's and Subaru spectra, derive abundances of many elements in a set of M dwarfs, but they also warn that many of the atomic lines are sensitive not only to the abundance, to changes in the abundance of that element, but also to changes in the abundance of other elements. So this is very tricky because then you cannot isolate lines and determine the abundance as we do for the FGK stars. And despite they manage to derive abundances, if you compare to the background points that are FGK stars, the errors are huge. So it's very hard to tell whether these stars belong to the thin or the thick disk, or well, how precise are these abundances. And you can see it's not only the abundance, it's the metallicity. Then there is the team by Soto et al. That have published a lot of papers using apogee spectra. And they have managed to derive parameters and also abundances. For example, in this work, 11 M dwarfs in FGK binary, so they can control much better the metallicity. And you can see, for example, how some lines, like these ones, iron or titanium or nickel, are very sensitive to changes in metallicity. The difference is from minus 0.9 to 0.1. However, other lines are not sensitive, and then you cannot use them to determine metallicity. More recently, this year, we also have this work by Jiacheng et al. Using very, very high signal-to-noise spectrum from Spiru of Barnard star. And they managed to derive several abundance elements, but they still show that there are many things not working. For example, here you have a spectra with a lot of lines that are not in the atomic data, so then they cannot be correctly modeled, so they are not in the laboratory data. It also happens the other way around, that there are lines in the models or in the synthetic models or in the atomic data that don't show in the real spectra. And we also have this work by Hassi et al., recent also this year, that use E-Green's spectra, which is another spectra but of a lower resolution. and also managed to derive individual abundances by fitting lines in a small wavelength regions of different elements for a planet host. So if you want to know more about the M-dwarfs, I recommend you to pay attention to these 3 talks that will happen today and tomorrow, where I guess they will talk more about this in detail. Okay, so just to finish, well, as I mentioned before, the high precision abundances are possible, especially for FGK stars. As a general rule, the closer your star is to the sun, the better. It will be easier. As you depart from the sun, from the stellar parameters, things get more and more complicated. Well, we have seen that the chemical composition of the protostellar cloud conditions the formation of planets, but also, although I haven't mentioned, the planet formation itself can affect the abundances of the stars if there are planetary engulfment events that happen across the evolution of the star. When you want to characterize your planet, it's very important that you do an homogeneous analysis of your star using the same tools and for solar reference spectra also to get your abundances. And with this, you will get rid of a lot of systematics that maybe can prevent to know what is going on there in reality. And then finally, so for the M-dwarfs, we have very promising results with high resolution spectroscopy, but it's clear that we need an improvement of the models and the line list. And also, it will be very nice to get more benchmark stars. So usually in the literature, what is done is to use M-dwarfs that have been observed with interferometry to obtain an independent measure of the temperature. And with this, we can establish if our spectroscopic methods are precise or not. And also, when you have M-dwarfs in binaries, together with an FGK, we can also constrain the metallicity. So it's important that we have more of these benchmark stars to better calibrate the spectroscopic methods. And this is all. Thank you.
We have time for a couple quick questions. is our next speaker. Please take it away. I'll give you a 2-minute warning.
So I'm a PhD, my name is Terese Olander, as introduced, and I'm a PhD student at Uppsala University, and I'm working on spectroscopy of M-dwarfs. And my work is within the Plato mission. Just to explain, this is 2 horses. That is a Dala-häst, a Dala horse. I picked that one because M-dwarfs are red stars, and they are complicated. And as you can see, this horse has intricate drawings on it because they are too complicated. Fun game. Identify the stellar line, the atomic line. This is an M-dwarf spectra in the optical, and these spectra are obtained from the CRIRES. So just so you know, the CRIRES have put available online a bunch of observed spectra. So if you go to that link, you can find a lot of spectra, both in the optical and near-infrared. I'm not going to put you out of misery. That is one atomic line, and I marked it in the line list below. And as you can see, it was very difficult to identify it because there are so many molecular lines. Same in the near-infrared. Where is atomic line? Fairly easy this time, right? It's that line. It's a silicon line. To be fair, a lot of the lines that you clearly see here are not atomic lines. It's iron hydride, which is not available in that particular line list. So just because it's an easy to find line doesn't mean it's an atomic line. So my work is within the Plato consortium, and Plato stands for Planetary Transits and Oscillations of Stars, meaning it's going to do light curves, basically. The primary objective is to find an Earth-like planet around the solar-like stars, but there are M-dwarfs in the sample. For the warmer stars, it's going to use astroseismology to characterize the host star, and there's over 250,000 stars, so prepare for a lot of exoplanets. Within the Plato work, we are building a benchmark database for all stars, type of stars that Plato is going to be observed, and we have M-dwarfs in that sample, and I hope that within a year there will be a paper about this. Plato is planned to be launched in 2026, so hold your thumbs. So in Plato, there's 25,000 M-dwarfs in the input catalog. Most are bright. And Plato is going to observe at least 5,000 stars, but this is still to be decided, so to say. However, astroseismology is going to be used on the warmer FTK stars, and we cannot observe the pulsations of M-dwarfs. So therefore, we cannot use astroseismology. And we're then dependent on ground-based spectroscopy to get all the parameters. But as you saw with the spectra, it's kind of a mess. The plot is made by Ulrika Heider, and it shows, part of the main sequence, so to say, of M-dwarfs that's included in one of the field of view. Within Plato, we also developed a pipeline. So it was developed first for the FTK stars. It was published by Gent et al. In 2022. And it uses Bayesian inference to obtain parameters, and it combines spectroscopy, photometry, interferometry, astroseismology, and sort of whatever they can throw in it. It's still under construction. They're still expanding it. And the spectroscopy part is using neural network based on the pane. So machine learning to interpolate between a grid of synthetic spectra. It has been tested, which you can see in that paper, on the Gaia benchmark stars, and is currently continued development by Catherine Lee in Heidelberg. We modified this pipeline to be able to analyze M-dwarfs. but we had to do a bunch of difference because we have to move to the near infrared, which meant we have to alter the normalization procedure. And we found a strong degeneracy between the surface gravity and other parameters. So we could not use spectroscopic surface gravity. We had to use photometry to constrain it. Since all of these modifications, we couldn't sort of look at the entire pipeline and modify the entire pipeline. We had to focus on the spectroscopic part. But we have a new postdoc in Uppsala called Nikki Miller, who's finishing the work and making it. The plan is to make it full Bayesian for M-dwarfs as well. So preliminary results, okay, this is not preliminary results. These are the results from the pipeline. We have not yet published it, but the paper is soon to be submitted. And as you can see, it is fairly good. There, we have two interferometry. So effective temperature and interferometry on the x-axis, and surface gravity and interferometry on the x-axis again. That star, that outlier, we believe that something is wrong with interferometry for that star. So it's a warning, do not just grab data just because it's interferometry doesn't mean that it's automatically good. Because all other spectroscopy results for that particular star agreed more with our result. So something is wrong with that interferometry. And it is in a binary, which is kind of sad. This is why I'm marking 2 stars. At the top, we have the fitted line. And you can see it's a good fit. We fit everything. We're using a line mask by Sarmento that was created for apogee spectra because we're using apogee spectra. Of course, we need to develop a better line mask, particularly for the Plato, what Plato's needs. Here is the result for metallicity. And it looks sort of like line shapes that we have some tendencies, but that's because we have the same star have multiple dots. And this is also a warning. You see there's a large spread just in metallicity. So yeah, you have to be careful when you pick your parameters. What about abundances then? If we get those, it's kind of difficult to compare your results when you don't have anything to compare with. But since we started this, there of course has been a couple of studies which Elisa also showed. But we are also working on it. So we are getting a benchmark abundances. So we have spectra obtained by the Giano spectrograph, which we reduced using reduce. And we removed telluric lines with a novel software called Viper. It was developed for the CRIRES consortium to calculate radio velocities. But in order to calculate radio velocities, you need to remove tellurics, and good for us. We're using turbospectrum together with a wrapper called TS-FitPy, and this is the latest version of turbospectrum. Marks atmospheric models, line list from Wald, and molecular line data from Bertrand Place. I haven't written here, but we are performing a differential abundance analysis. So we're analyzing a solar spectrum with the exact same line list, and then we're subtracting the solar result from the M-dwarf result on line-by-line basis. I just added this slide during Elisa's talk, just so you know. That's why it's sort of very rough. This is the fit of a silicon line, with the orange and black being the M-dwarf, and the blue and the red being a solar spectra. The red is the observed spectra, and the black is the observed spectra. As you can see, there are some issues here. So I don't remember if I picked exactly this line when calculating the total abundances of silicon, I think I didn't, because we have telluric lines, which affect the fitting of the solar line. And you see this difference. I think it might be related to non-LTE, but it could also be bad data in the line list. Just for information, these are features from the telluric removal, because we were removing the telluric from the M-dwarf spectra, but we couldn't do it for the solar spectra. And when you remove strong telluric lines, often there is some weird artifact left over. So those areas you cannot fit at all. And here's our result, very, very preliminary results. For the metallicity, we sort of look kind of okay. The silicon, you can see that our errors are really, really big. This is partly because of what I showed in the previous slide. But this is preliminary results. We still need to do a more thorough analysis, basically going into more detail of each line. But this is a very time-consuming process. But the plan is to basically get iron, the metallicity, the iron, get silicon, then analyze titanium, then go back to silicon, because elements are connected, as you heard by Elisa. Difficulty we get into? Well, non-LTE effects doesn't only exist in FTK stars. We find them in M-dwarfs as well. And we need to investigate more about this. I know, for example, I haven't put in the reference, but potassium has a clear non-LTE effect in M-dwarfs. And magnetic fields, especially for M-dwarfs, it affects them pretty much. You can go around it by choosing stars that don't have that much strong magnetic field, but you can't do it for all the time. The connection between abundances, for example, titanium and oxygen combined for titanium oxide. We have the continuum effects that Elisa was talking about with the donors to the donating electrons affecting the continuum, and we have water molecules affecting the continuum. And as I said, the titanium line, or the silicon line, I'm not sure if it's non-LTE effect or if it is bad atomic data. I still need to check that. Thank you very much. And yeah, I'm gonna finish soon, so yeah, thank you.
Okay, we have time for probably a quick question. So our next speaker is Giulia Mraz. Yeah. Take it away. I'll give you a 2-minute warning, and if you want to maybe use the hand mic to be safe.
safe.
Should come up. Okay. Awesome. So, hi, I'm Giulia Mraz. I'm a first-year PhD at McGill University, and I'm going to talk a bit about a CO detection on the night side of WASP-33b. So throughout this talk, I'm mainly going to be talking about ultra-hot Jupiters. So if we see here on this graph, on the y-axis, I show planetary radius, and on the x, I show period in days, and it's colored by equilibrium temperature. So the ultra-hot Jupiter regime is around here. It's planets that have less than around 2-day period, and a little bit more than about a 1.2 planetary radius in Jupiter radii. So the important thing to know about ultra-hot Jupiters is that they have strong stellar radiation from their host star. And the stellar radiation could be about 100 times that's seen in its hot Jupiter counterparts. Additionally, ultra-hot Jupiters are typically tidally locked. So we have that day side that faces the planet at all times. And this creates a really strong temperature difference between the day and night side of these planets, and could be over about 1,000 Kelvin between that day and night side temperature. So as we've seen, typically when we look at these atmospheres, we're looking at pressure temperature profiles, something like this blue line here, where we have decreasing pressure with decreasing temperature. However, when we're referring to ultra-hot Jupiters, we typically see thermal inversions, where portions of the atmospheres increase in temperature with that decreasing pressure. So our temperature-pressure profile looks something more like this now, this red line, showing that thermal inversion, whereas that non-inversion is blue. So this is actually typical to see on the day side of ultra-hot Jupiters, to see that thermal inversion, whereas on the night side, we typically see that non-inverted profile. This is pretty distinct in emission spectroscopy because we will see an emission signal for a thermal inversion, whereas for a non-inverted atmosphere, we'll see an absorption signal. So for example, on a day side thermally inverted planet, we would see CO in emission, whereas on the night side, we would see it in absorption. So one planet that's thought to have these thermal inversions is WASP-33b. So again, if we see my graph here, where y-axis shows planetary radii and Jupiter radius, the period shows is on the x-axis. We see WASP-33b is right in the middle of that ultra-hot Jupiter regime. So important things to point out is that the planet is really hot at about 2,700 Kelvin. 2,700 Kelvin. The period is around 1.2 days, and it has an inflated radius of about 1.6. Important stellar parameters is that it is an A-type star. So it has stellar pulsations, and it's a really fast rotator. So WASP-33b has been observed previously, and there's been 3 space-based observations on this, 2 from Spitzer and 1 from HST. And here I'm showing the results from a study in 2015, where we're looking at one of the first evidence that we're seeing a thermal inversion on WASP-33b, where the green points here are showing the data of HST, Spitzer, and ground base. That red line here shows the model of a thermal inversion, whereas the blue shows that non-inverted atmosphere. And this study was hinting towards the fact that we actually will have this thermal inversion on the day side of WASP-33b. Additionally, we've had some ground-based observations of WASP-33b, where we see Aries, Giano B, Keck, and Spiru. And here I'm showing a GCM from a study in 2023, where it's showing that night side of that non-inverted atmosphere, and is predicting that day side to have that thermally inverted atmosphere on WASP-33b. In addition, TIO and VO can cause these thermal inversions, and this was actually detected in WASP-33b in 2021. So in these observations, most have looked at the day side of WASP-33b, and not a lot have looked at the night side. Typically, when we look at the night side of planets, we do this using phase curves. So one of the phase curves that we've actually been able to see this thermal inversion in is WASP-121b, which was done in 2022 on HST. So I'm showing the results here where they see this H2O as a thermal inversion on the day side in that top portion there, and on the night side it's seeing H2O in absorption. So this is one of the phase curves that we can actually see both temperature profiles there consistently. Whereas from ground-based astronomy, we've only had one tentative detection of the night side of any planet, which was known as HD 179949b, and this was done really recently in 2024 to actually get that ground-based detection of the night side of any planet. So we propose to actually look at the night side of WASP-33b to see that non-inverted atmosphere, or hopefully see. Here I've listed out the nights, where the dates here, the phase coverage that we had, and my circle here shows our phase coverage, where the black shows a typical transit of WASP-33b, which was about 3 hours. Below I show the mapped out phases, where orange shows that day side and blue shows that night side. So we had 3 pre-transit observations and 2 post-transit observations. Our data was taken on the Canadian-France-Hawaii telescope, which is on Mauna Kea in Hawaii. We used the near-infrared spectrograph known as SPIRU, which has a wavelength coverage of about 0.9 to 2.66 microns. Resolution's about 75,000. And for any pure pre-processing, we use the Apero pipeline. To actually extract our planetary signal, we use the open source pipeline known as Starships. So Starships is designed to extract this planetary signal, and it does this through a series of steps. So I'm only going to briefly run through this pipeline, but please feel free to come up to me later to talk more about it. So we're going to run through the reduction, really quickly looks for tellurics as a function of orbital phase, normalizes the spectra. We can divide it by our reference spectra, and it uses PCA to correct for those remaining vertical residuals. From here, we can actually run free chemistry retrievals, which use Petty-Red-Trans, ECM, MCMC to explore that parameter space. And this will actually be used to produce our best fit models, which can then be used in our cross-correlation. So for cross-correlation, we followed cross-correlation to log likely mapping methods. And for our significance, we use a Welch t-test, which evaluates that null hypothesis that 2 samples were drawn from the same distribution. So moving on to our results, these are our best fit models here from our retrievals. So we ran it with 2 different temperature profiles. We used a GEO profile and a modified GEO profile. In our GEO profile, we only used the abundance of CO, whereas the differences in our modified GEO, we included abundances from Fe, OH, and H2O. My corner plot here, the top shows CO abundance, whereas we have VRAD and then KP. We can see here that in both profiles, we see that abundance in CO. They're relatively similar. Here, where the modified GEO ends about there, and our GEO profile has a bit of a higher abundance shown for CO. So for the remainder of the presentation and for my cross-correlation, I will use the GEO profile here. And we can also see our line intensity here shows that it should be an absorption based on our retrievals, with wavelength being the x-axis there. So for a reminder, we had 3 pre-transit observations and 2 post-transit observations. So we've combined these separately to actually increase our signal-to-noise ratio. When we combine our pre-transit nights here, that's again nights 1, 2, and 4, we don't see any detection here of CO and absorption. And our t-test below actually confirms that non-detection pre-transit. However, when we look post-transit here, looking at nights 3 and 5, we can actually start to see that detection there of that stark yellow line that's right here in the center, showing about a 6.6 detection of that CO and absorption post-transit. And that's actually confirmed with our t-test that's below. Right before it, what you might see is this dark line right under it. That's evidence or tentative evidence that we're actually seeing CO in emission right before it blue shifted. And the thought is that this might be coming from the day side of that planet. As we can kind of see some here, it's evidence that we may be seeing some of that thermally inverted atmosphere on the day side, right, blue shifted right before that CO and absorption. So because we've combined the nights, it'd be interesting to see these nights out one by one to see if we still get that detection in each night. So if we have our combined nights here of nights 3 and 5, we can look at each one individually, seeing that night 3 still shows that detection of CO and absorption with evidence of CO and emission. And similarly for night 5, we again see that CO and absorption signal, again with the tentative evidence of CO and emission. Both show a detection of about 4 sigma here. So as a quick summary and conclusion here, if we're looking at our planet that orbits our star here, with the night side here, and the day side that passes behind, we know from previous observations that there was a thermal inversion on the day side of WASP 33b from both ground and space-based observations. And we can see this in CO in emission. Whereas when we look, normally when we want to look at the night side of these planets, we need to use phase curves, whereas there's been one previous detection of ground-based observations of the night side of a planet. So we proposed to use the night side to observe the night side of WASP 33b, and we did this doing 3 nights pre-transit and 2 nights post-transit. So pre-transit, we saw a non-detection of CO and absorption, whereas post-transit, we saw that detection of CO and absorption at about 6.6 sigma with a tentative detection of CO and emission. That tentative detection hints that we're actually seeing that day-side thermal inversion blue shifted before CO and absorption. So this could actually be this non-detection pre-transit and this detection post-transit could be indicative of actually seeing that eastward jet that is thought on ultra-hot Jupiters, where we have that colder atmosphere pre-transit and a bit of a warmer one post-transit here, showing that non-detection to that detection post-transit. Additionally, because this is the second observation that we've seen from the ground of a night-side atmosphere, this could be an economical way to actually constrain vertical temperature profiles of exoplanet night sides without having to use phase-resolved spectroscopy. I will leave this up while I answer any questions.
Okay. Right. Okay. Hello, everyone. I'm Jiacheng from University of Bologna. So today I'm gonna talk about my current project, which is about the protoplanets. So I'm supervised by Leonardo Testi and Lorenzo. He's here also. Okay, so let's start from protoplanets. So I think we all agree that they are very charming objects in our universe because protoplanets are very close to the birth moments of planets and the planetary system, and therefore become the best targets to study the initial composition of a planetary atmosphere and to constrain the planet formation scenarios. And it's been a long time that we find some indirect evidence by kinematic features such as the rings, the gaps, and the turbulence of the disk structures by the disk observations that indicate the existence of planets embedded in protoplanetary disks. And thanks to the amazing high contrast imagers we have HiRISE and Sphere right now, and METIS upcoming, it is kind of sure that more and more protoplanets gonna be detected and imaged. So here I show the famous PDS-70 observed by the Sphere on the left. Okay, use this on the left, and the very fresh near-com result just came out this year. But the HCI can resolve the special separation of protoplanets, but it is kind of lack of special resolution, as you can see from the SED of PDS-70B. The Sphere AFS is in a very low spectral resolution. But on the other hand, in terms of characterization of planets, high-resolution spectroscopy is already widely used nowadays for evolved planets. I put here two examples, one for the Mascaro 1b and the other one for Beta Pictoris b. They are all observed by CRIRES+. So can we combine the HCI and HDS together to characterize protoplanets instead of just understand everything from the images? To understand this question, I am developing a synthetic observation pipeline on CRIRES+ to study the feasibility of this kind of observation. So here the flowchart shows the general structure of my pipeline. It's a bit complex, but we can break it down. So at first, it is associated with the ETC from ESO. So as always, when you prepare the observation, you need to set up your ETC parameters. And from the HCI observation, you have the measurement of flux contrast, and therefore you can derive the apparent magnitude of your favorite protoplanets. And for the input SED, we choose the phonics for protostars and the BT settle for planet. But pay attention here, the extinction is a kind of important factor because we assume that the planet is embedded in protoplanetary disks. So what we input actually is the extincted spectrum of planet. And ETC gives you the PSF profiles, the extracted spectrum, and also the tellurics. But this is not the end of this story. So what missed there? So first, for this kind of observation, the star and the planet are observed as two separated PSF. So the spatial separation is very important. It's kind of essential factor to affect the detectability of protoplanets. And moreover, the noise is not, the noise distribution is not in the ETC, and it doesn't simulate the noding and ABBA subtraction that we always use for infrared spectroscopy. So the pipeline will reconstruct the 2D spectrum and combine all signals contributions together and run the subtraction of sky background and the stellar signal. In the end, it runs the cross-correlation also to make some analysis and some atmospheric retrievals also. Okay, so we tested this pipeline with planet candidate 169142b. It is already observed by Sphere. These images are from Sphere. So we have the flux contrast, then we have the apparent magnitude of the planets. And it is like 37 AU away from its host star, so it's capable to be spatially resolved by CRIRES+. And for the ETC setup, we choose K-band and L-band to study the feasibility, and we ask for 1 hour of the integration time, which is kind of normal for this kind of observation. Okay, so we input 2 spectra into the ETC. This one is the phonics spectrum for the host star, and then the orange curve shows the best fit extincted spectrum for the planet. The extinction law is now from the ISM extinction, but for sure we need to consider some alternative extinctions in the future. So we pass them into ETC, and then we try to reconstruct the 2D spectrum, and this is one example for one exposure. And then the pipeline runs for the noding and the ABBE subtraction to remove the sky background, and then make a sum stacking for all exposures together. And you have a final 2D spectrum like this. And then thus you can feed the PSF and then remove the stellar signal from the position of planet. And hopefully you can get like a very noisy spectrum as shown as blue curves here. And the planet signal is completely embedded in this sea of noise. This is normal for high resolution observation for exoplanets. So that's also why we need cross correlation for this. But before heading to that direction, we can already estimate two things: the flux contrast and the cross-correlated signal-to-noise ratio. So as shown here, for K-band, the signal-to-noise, the cross-correlated signal-to-noise ratio is around 12.8, and for L-band, due to the very strong sky background, the signal-to-noise ratio is down to 4.6, more or less. But it is still very optimistic to observe this planet with high-resolution spectroscopy, in particular with CRIRES+. Okay, so at this moment, I really want to show you some preliminary results for the cross-correlation, but unfortunately, I found out some bugs in my program, so I put it here for on one of my next steps. And by the way, we calculate the high-resolution model spectrum with Sorona line list, so we're gonna cross-correlate with our model spectrum, which is nice. And another important thing I want to mention is, so we have a simulation pipeline, and thus we can play with parameters, right? So we can explore like the planet with different scenarios and with different orbital architectures with this simulation pipeline to understand the general detectability. For example, we have a nearby star-forming region, the Scal-Centaurus, which is 100 PC away from us. And imagine we have like a 5 million year old protostar with some disk extinction, and then with a planet 40 AU away from the star. Is it possible to be observed by CRIRES+? And if the answer is yes, then what is the limit of CRIRES+ in this kind of observation? All of this will be explored by this simulation pipeline. And of course, I also need to polish this simulator to get closer and closer to real observations. For example, to include the variations, the time variation of sky background, and like to include some systematics. And at this moment, I'm still not sure if we can simulate them or not. Anyway. Okay, so in the end, I show my horse here. It's a horse running on a very hot protoplanet. And I hope in the end you can use this pipeline to characterize your famous, your charming, your favorite protoplanets. And it's time to bother our DPR reviewers for the real observation with this pipeline. Okay, thank you.
And it's a pleasure for me to introduce to you Arthur Vigan, who will speak, maybe.
It was working earlier, so I don't know.
Okay, it's working. He will talk about on instrumentation of high-resolution spectra of exoplanets. So
can I use? Yeah. Okay. Okay. Thank you very much. So I have the difficult task to try to summarize a bit the status of the instrumentation to do high-resolution spectroscopy for exoplanets. And actually, while preparing the talk, I realized that it's quite a broad topic, so maybe I will forget some things, and maybe there are things to add, but I'll try to give you a good overview. So this is very classical plot. I'm not going to extend a lot on that. You are seeing the different families. Oh, sorry. Ah, okay. Okay, sure, sorry. The different families of planets that have been detected by the different techniques. But of course, from the instrumental point of view, what is more interesting is when you translate that into observables. So what matters here, you are seeing two things. This is the same plot as before, but I've transformed the different planets in terms of observables, and what you are seeing are actually two kinds of information. The emitted light for all of the planets. So obviously for the young giant planets that have been detected by direct imaging, this is really the light that they are emitting because they are still young, they are still warm. And for the much closer in planets, this is because they are very close to the stars. So this is the ultra hot or hot Jupiters that we've been talking about. And they are re-emitting a lot of the light that they are, because they are strongly irradiated by their star, and they are re-emitting some of that energy. And of course, after that, you have the reflected light part, which is, of course, completely negligible for those distant companions. They are at contrast of 10 to the minus 10. So I didn't mention, but this is the contrast between the star and the planets. But of course, for much closer in planets, this reflected light part is actually at levels that are probably detectable. And in fact, if you compare to the spectral the diffraction limit of the largest telescopes that we have on the ground, you have sort of two categories. You have the resolved spectroscopy on the left, on the right, and you have the unresolved spectroscopy on the left. And in fact, if you look at what has been done so far in terms of observations, well, on one side, there are some results that we've heard about in the morning. Those are planets that are detected sometimes in emission, sometimes in reflection, a bit of both, so that's quite interesting. But basically, you are not detecting the planet itself. You are accumulating a lot of photons on the star and the planet, and then you are trying to disentangle between the two. On the other side of the plot, we are in the resolved spectroscopy part, so we are separating the star from the planet. And when you look at that from, let's say, the data point of view, well, you have the star that is dominating. So usually in a seeing limited case, which is often the case for most spectrographs that we've heard about this morning. And at a much, much lower level, you have the planet. So here at a contrast of about 10 to the minus 5. And when you are in the seeing limited case, you rely only on your high resolution spectroscopy post-processing to detect the signal of the companion. So you have to rely on high resolution to remove this factor of 100,000 to detect the planet. But as soon as you start improving your instrumentation using some adaptive optics, for instance, low-order adaptive optics, you start concentrating the energy both for the star and the planet, and here your instrumentation starts to play a role, and you gain already a factor of about 500 at the position of this planet, and you only have to rely on the post-processing for the remaining factor 200 or 300. And of course, you can use even better systems with a high-order adaptive optic system, what we call extreme AO sometimes, and in that case, you gain even more. This time, your instrument allows you to gain a factor of about 10,000 in terms of contrast, and you only have a factor of 10 or 20 for your post-processing. And on top of that, if you had a coronagraph, so the role of the coronagraph is to remove the diffraction of your instrument, and in that case, the post-processing factor becomes even smaller. So if we go back to that plot, well, on one side, what we want to do with unresolved spectroscopy is basically to accumulate as many photons as possible from both the star and the planet, right? Because you cannot separate them on sky. So what you want is pretty simple. You want a big telescope. On the other side, when you go to resolve spectroscopy, it becomes a bit more complicated because you want to resolve the system. So what you want to do is collect as many photons from the planet as possible while rejecting as many photons as possible from the star. And so in that case, you have to rely on much more complex instrumentation that involves, of course, a big telescope plus adaptive optics plus sometimes coronagraphy. And of course, in both cases, you have to rely on the high-resolution spectrograph. So let's first have a look at the unresolved spectroscopy case. So in that case, what you are targeting usually are hot or ultra-hot Jupiters, which are fast-moving objects. We are talking about kilometer per second motions on their orbit. And so in that case, any good cross-dispersed HL spectrograph will actually do the work as long as you have, of course, a certain amount of stability on your PSF. So here I've taken the example of the Espresso, which has 2 channels, but of course this works also with a simpler design with a single channel. But usually you feed the light of your spectrograph, usually from a fiber. You have a collimator on your HL grating, which will separate the different orders in your data. And then you have a cross-disperser that will again, disperse the light, and you will end up with several orders on your detector. And in that case, most of these spectrographs, they are optimized for planet search. So they are highly stable, but they are usually fiber-fed with multimode fiber because they are usually seeing limited instruments. So in that case, you have to use methods like scrambling or octagonal fibers to make sure that you have a uniform illumination in the fiber and you have a very stable PSF at the entrance of your spectrograph. So of course, this has had some complications. I've put a few examples here with scrambling and with octagonal fibers. But in most cases, as I said, you are seeing limited. But okay, so there are many such instruments in the world. Here are a few examples. I'm sure I've forgotten some of them, but what is really nice is that they cover both hemispheres at different resolutions, both in the visible and the near infrared. So it's quite a broad range of instrumentation. And here are a few images. You see some familiar names, and you see that one thing that they have in common, well, except for the fact that they are in a cryostat because you want to be very stable. The one thing that they have in common usually is that they are very big. They are huge instruments. We are talking about cubic meters and tons, right, for this kind of instrument. And in fact, you can understand that when you go to sort of fundamental equations for spectroscopy. So here you have I have expressed the resolution as a function of different parameters. Some of them are quite obvious, like the diameter of the telescope, the wavelength, but some others, well, this phi here is the angular slit width or the size of your fiber, if you are on a fiber-fed spectrograph. And of course, you see that if you are, this is basically fixed by your observing site. If you are in a SIGINT limited case, this will be of the order of 0.5 or 1 arc second. So this parameter is fixed, and if you want to go to high resolution, then the only parameter you can play on is the size of the optics, the size of your beam on the disperser. And it means that if you want to go to high resolution with seeing limited spectrographs, you end up with pretty big optics and a pretty big spectrograph. And what happens when you go to the diffraction limit, then of course phi becomes the resolution element of your telescope, so lambda over d. And when you replace that into the equation, then your resolution becomes much, much simpler. And in fact, it becomes independent of the telescope and the slit size or the fiber size. And it means that you can design your spectrograph completely independently from your telescope. In the focal plane, this is what it looks like. A multimode fiber, they are usually, well, about 100 micron across with a very big core that is around 0.5 to 1 arc second on the sky. But when you get closer to diffraction limits, well, you can go to much smaller fibers, single mode fibers that have a very small core, typically 5 to 10 microns, that represent approximately 1 lambda over d on the sky. And of course, the same reasoning is also valid if you are using a slit spectrograph. So of course, slit spectrographs are a bit less common now than they used to be, but this also applies if you have a slit. And going again to the plots I was showing earlier, well, in the seeing limited case, What you want to do is integrate as much photons as possible from the whole system. Well, you don't have the choice because you're seeing the PSF of your telescope is huge, and you cannot separate the star from the planet, so you have to integrate both, right? Then you start putting some low-order adaptive optics, so you are concentrating the energy from the star and the planet, so you start to be able to disentangle the two. So these kind of adaptive optic systems are the ones that we've had since the early 2000s, that provide Schrell of the order of 40 to 50% in the near infrared, and they have been pretty efficient at providing really nice results. So I'm showing here a few of them. Some of them are quite old, like on Beta Pictoris B with the old CRIRES, and but this has been reobserved more recently. There has been also things done with integral field units, Symphony, Osiris. So that was already a very, very good start. And now, since approximately 10 years, we have these high-order extreme adaptive optics that provide a much better Schrell, and we end up with instruments that are diffraction limited in the near infrared. So in that case, we can use coronagraphy, and we are able to really separate the star from the planet. And of course, you can put your single mode fiber, but obviously what you are interested in here is not the star. So you move your single mode fiber on the PSF of the planet, and you become able to sample directly the light of the planet. So of course, the planet is still a bit lower than your speckle floor or your stellar halo, but still you have much less signal to remove to access the spectrum of your planet. If you look at the situation a few years ago, so we had these really nice high contrast imaging instruments that allowed to reach contrast of the order of the million, but only providing very low spectral resolution. Because these instruments, they were not designed to really study and characterize exoplanets. They were mostly designed to detect exoplanets. So they are spectral imagers, so they provide low resolution spectroscopy, but also you have the full field of view. You have the full spatial information to be able to look for planets, right? And on the other side, we have the high-resolution spectroscopy. Here I've put only the example of Beta Pictoris, which was the highest contrast reached in a few years ago. And since then, of course, the situation has changed a bit. Well, interferometry with gravity has started to play in this field and characterize some companions at these resolutions down to, well, approximately this contrast. But what's more interesting is that in the past few years, there has been new developments of instruments coupling really high contrast imaging with high resolution spectroscopy. So you've probably heard about high dispersion coronagraphy. Well, for me, this term is probably not completely right because in most cases, actually, these instruments, they are not using coronagraph. So I think it's better to talk about the combination of high contrast imaging and high resolution spectroscopy or high contrast, high dispersion. I think it's more appropriate. Anyway, these three instruments, they share many things in terms of design. So obviously, they are using large telescope and good adaptive optic system, extreme adaptive optic system. And then, so this is like the basic things that you need. Then they are implemented as an addition where you are picking up the light of the planet with an injection module. So here I've put some images from the HiRISE instrument that we commissioned last year, but we could put similar images for the two other instruments. Then you have the fiber link. So this fiber link can be a few meters long or actually quite long for 80 meters for the HiRISE instrument. And then you have an extraction module at the entrance of your high resolution spectrograph that reimages the output of the science fibers at the entrance of the spectrograph. And so these instruments, they are really nice because, well, they cover, as you can see, a broad range of resolution and also different wavelengths. So they are very, very complementary. So the design of these instruments, they are really at the, I would say, at the front line of the research and development in terms of instrumentation. And of course, there has been a few challenges to design this kind of instrument. The main challenge that they share is that the overall challenge is the end-to-end transmission. Here I'm putting the transmission budget for the HiRISE instruments, and you can see that there are many components coming from the atmosphere, the telescope, the instruments, and actually one in particular that I'm going to talk about are the fibers and how you can inject your light into the fibers. But anyway, in the end, you end up with a transmission of a few percent, between 3 and 4%. So it's very, very low throughput. So this is why you have to optimize these whole systems to maximize the throughput in the end. And so talking about fibers, of course, we talked about single mode fiber. And what you want to do is actually to feed your telescope PSF, which is diffraction limited or almost diffraction limited, that is very complicated. It has hairy rings, the diffraction of the spiders, optical aberrations, and what you want to do is to feed that into a single mode fiber that can only transport a quasi-Gaussian electromagnetic field, right? So when you overlap the two electric fields, you sort of see that it matches, but it's not perfect. And in fact, when you look at that in log scale, well, you see that there is a complete mismatch between the two. So it means that you will never be able to feed the whole light of your telescope in a single mode fiber. And when you compute what we call the overlap integral, and to compute what's the injection efficiency, so how many photons you can actually, or the fraction of photons that you can feed into the fiber, you see that with only the pupil of the telescope, the VLT in that case, you can only feed about 75% of the incoming light. So you're losing 25% of your photons. And as soon as you start adding some aberrations coming from the atmosphere, from the instrument, you will lose again. So in the end, you end up with about 60% of the incoming photons. So this is really, there is a strong influence from both your telescope and your instrument. But this is, of course, if you are perfectly centered on your fiber. As soon as you move a bit away, so if your PSF drifts a bit in front of your fiber, you end up losing a lot of light. And so the centering is really critical. And typically, the instruments I was talking about, they have a specification of being centered better than 0.1 to 0.2 lambda over d, because after that, you are losing too much flux. And so what does this 0.1 lambda over d represent? So here you are seeing the same PSF as before. There's a zoomed in version at the right. And when you overplot your single mode fiber, well, the big white circle is just the fiber cladding. The core itself is equal to 1 lambda over d. And 1 lambda over d, well, what you want to do is actually center the PSF within that small red circle. So this is, from the instrumental point of view, this is a very big challenge, because keeping the PSF that is coming actually through the atmosphere, so you have to correct for the aberrations of the atmosphere with your adaptive optics system, this is a very serious challenge, right? So this is probably the main challenge that these instruments had to face. Of course, this didn't prevent this instrument from being designed and actually integrated and tested. So here I'm showing a gallery of some results that have been out now for relatively recently. And actually, what is really interesting is that now, if you take the example at the bottom, so this is actually quite a bright brown dwarf. But what you see is that with this kind of instrument, you have the full data in black, and then you can decompose between the companion model and the stellar model. And now you can see that the level of contamination by the starlight is actually below the level of the signal of the companion. So it means that you have inverted compared to unresolved spectroscopy, where the stellar signal is completely dominating. Now in some cases, we are in a case where the companion signal is dominating. So this is a completely change of paradigm for these young companions that couldn't really be characterized before. So okay, this field of instrumentation is quite active. So what's next? So what's next is that because you are feeding them with single mode fibers, then as I mentioned earlier, you can go to very compact spectrographs that have been designed completely independently of the telescope. And so here, well, basically you can go from CRIRES, which is 7 cubic meters, 6 tons, that covers only 50% of the H-band in a single observation, to something that looks like this, which is, well, you can almost lift it with one person, maybe 2 persons, that has approximately the same resolution, and that covers the full band and at a much, much higher throughput. So these are developments that are ongoing. I mean, you can see this is an existing spectrograph that has been tested on Sky. And there are other developments. So most of the things that I'm showing here, they are still at the level of research and development. Some of them have been tested on Sky. But it's still not implemented in what I would call facility instrumentation, but this is coming in the coming years, right? So this is really a very active field in terms of instrumentation. So talking about facility instrumentation, there are many developments ongoing. One that I would like to talk about a little bit is the Ristretto project, which is very interesting because it's an extreme adaptive optics system in the visible that is designed to target Proxima Centauri b in reflected light. So of course, this is super challenging. You need a big telescope. You need a super fast adaptive optics system, fibers, and a dedicated spectrograph. But okay, simulations have showed that it's probably feasible to detect this planet in reflected light. Of course, there are other planets that could be detectable, and so right now the spectrograph is in the procurement phase, I think, and but I think there is still a long way to go for the adaptive optics system for such an instrument. But anyway, I think that's a very interesting project that we need to follow in the coming years. After that, of course, well, let's talk about ELT instrumentation. And I'm very sorry for my American colleagues, but I'm going to present a very biased view because the ELT situation in the US is a bit more complex than it is in Europe. So I'm sorry. All right. So with ELTs, you gain a geometrical factor of about 4 to 5 just because you are going from an 8-meter telescope up to a 40-meter telescope, right? So geometrically, your PSF becomes much smaller and you have access to much closer angular separation. Of course, this is only valid if you are using adaptive optics, but fortunately for us, the European ELT, it will be AO by default for all instruments, all first light instruments. And here I'm showing a plot with the different resolution and spectral coverage of all the first light instruments. You can see that it's pretty well paved, and there has been already some studies, for instance, for the Harmony high contrast imaging module. I encourage you to see these talks or chat with these people. Oh, I'm sorry, I forgot the name here. I feel really bad. But anyway, we had a poster this morning. I go see that poster. That's super interesting. And as a second generation, what will be coming in maybe 10 years from now is the planetary camera and spectrograph, which will be an extreme adaptive optic system with coronagraphy, with an IFU and also a fiber-fed spectrograph, and all of that optimized to try to detect telluric planets in reflected light in the visible or very near infrared. So of course there is still a very long way to go to design this kind of instrument, but clearly this is already on the roadmap for the ISO ELT, right? So this is also something to follow in the next years. Finally, what about space? Okay, so I did a little bit of a back-of-the-envelope calculation for a solar-type star at 10 parsec with a planet, telluric planet at a 10 to the minus 10 contrast, with some reasonable assumption on the instrumentation, and exposing for 1 full day. So how many photons do you think we get at a resolution of 100,000 in 1 day? Any guess? Very few. All right, so we are talking about less than a photon per day. So I think, do we really need high-resolution spectroscopy in space to detect or characterize telluric planets? That's a question. Maybe more generally, the question is what kind of future high-resolution instrumentation do we need for what science? And I will leave you on that. Thanks for your attention.
Any question for Arthur? About HiRISE, a new instrument to characterize exoplanets. Please stay here because there is the camera there, and I will tell you when you miss 2 minutes. You can use this. So,
All right. Hi, everyone. My name is Jean. I'm a research fellow at Queen's University Belfast, and I'm going to talk about HiRISE, which is a new instrument to characterize exoplanets. You've heard of it already, and I'm happy to present to you the first result of this HiRISE survey. Obviously, for such an important project, lots of people are involved, either in the instrumental consortium side or for the survey, where we have people obviously observing and analyzing the data. So thank you to all these people. First, what is HiRISE exactly? Again, you've heard of it already, but in the VLT, on the UT3, we have one nice instrument called SPHERE, which is a high contrast imager. And with SPHERE, we can directly see some of the companion, thanks to extreme adaptive optics, coronagraphy, a wide spectral coverage. But one of the downside of SPHERE, it's its relatively low spectral resolution. Now, on the other side of the UT3, we have another instrument called CRIRES Plus. It's a high-resolution spectrograph, and while it doesn't have any adaptive optics or coronagraphy such as SPHERE, it has a very high spectral resolution. Now, the goal of HiRISE is to take both of them and to link these two instruments together in order to get the most of it. So by coupling SPHERE with CRIRES, we can better distinguish between the star and the companion, allowing us to better analyze the exoplanets. So what do we see with HiRISE? So let's look at our first observation that we made during our commissioning last summer 2023 of the brown dwarf HD 984b. Here you see an image of the HiRISE film, so the fiber injection module. And in the center, you can see the saturated star. Now we want to look at the companion, so you may guess it's the brightish spot on the right, but actually this is just a ghost. I'm going to come back on that in a few moments. Now, the companion we are trying to see, it's over there. So obviously completely hidden in the spectral noise, in the stellar noise. And that's the one key point from the HiRISE, is that we have to know exactly where the companion is already, so that we can blindly put our science fiber onto our companion. But assuming everything goes well, we have the right number, and we know exactly where to put our science fiber, this is what we would see. We would have the flux coming from the companion onto a science fiber. Over there, we can see the nice terrex and everything. Now, something we didn't notice, something we didn't expect, and that we found out during our commissioning, is that just below the science fiber, the flux coming from the companion, we had another bright flux, and we didn't know what it was. Well, this is a ghost I was telling you about earlier, and this is actually due to the AO guiding star leakage. Now, this may seem problematic, and we are maybe planning for a future intervention to remove this ghost or AO guiding star leakage, but actually it's not that dramatic, because this leakage is the same whether you are observing the companion or a background. And so by just doing one minus the other, you're removing the ghost and you're removing all the bad pixels, and you're left just with the flux coming from the companion. All right, so we see that, and now using our custom-made pipeline where we do the calibration, filtering, extraction of the data, we were able, during our commissioning, to confirm our first detection at the exact velocity where it was supposed to be, and with the same broadening as we were measured from other instruments. So we were happy. Finally, HiRISE is working. Great. We can now start to look at exoplanets, characterize them, find their broadening, rotational velocities. But first, before showing you the result of our survey, I'd like to take a few moments to discuss some of the challenges we have with HiRISE. I already talked to you about the fact that we need precise measurement of the companion to put blindly the fiber on top of the companion, but there were other challenges. One of our biggest and current challenges we have is the wavelength calibration. Because after observing a companion, and after using the ESO CRIRES pipeline, we noticed that there were still a few issues with the wavelength calibration. The wavelength wasn't perfectly calibrated. And why this small shift looks small, actually when we are looking at the CCF, you can see that instead of having a nice peak in your CCF, you now have a broader one with some kind of double peak. So not only this type of double peak CCF can mess up with the measurement of your radial velocity, but it can also mess up with the measuring of the Vigan I, and also, if you're doing some retrievals, it can lead to some biases. So correcting for this wavelength calibration is a very important step. All right, so one of the simplest solutions to correct for this wavelength calibration issue is to use a TRIC template, because we know precisely where the TRICs are. And so, by just comparing observation with some TRIC template, we can recalibrate each individually each order one by one to get, we're using quadratic recalibration to get a perfect wavelength. So this idea works well for most of the order, except that for some of the order we're observing, we have no TRICs at all. So whatever TRIC template you're using, there will be no way for you to recalibrate your order with this. That's why on top of the TRIC template, we had to add an M-star template with M-star observation, because M-stars have deep stellar line that can be used as well to recalibrate our wavelength. So we have combined both a TRIC template and an M-star template to recalibrate our data. We have built our pipeline around that using nested sampling, and that work was led by Romain Cadet, which is a master student at LAM. And you can see below the result of our recalibration, where each wavelength, each order of our data set had to be recalibrated individually, and as you can see, each order have a different recalibration. That's why it's important to look order by order, and that's why it is important to both use TRIC template with M-star template. All right, so I presented you our the commissioning of HiRISE, which went well. I've shown you a few issues we had to correct for. Now I can start presenting you our survey. So first, what are we looking at? Well, so far we have been looking at both brown dwarf and exoplanets. Some targets are a bit easier or relatively easier to observe because they have a higher SNR, while all the targets are a bit more difficult because they have a low SNR. Now, so far we had 4 nights of observation in November, 1 night in April, 3 nights are coming up in August. And for each target, we have been observing between 2 to 3 hours, because not only we have to observe the companion itself, some backgrounds, but also the star and some background of the star. And finally, the goal of this HiRISE survey is obviously to estimate the radial velocity of the target, so that to constrain its orbit, to have better measurement of the orbit of these targets, to also measure the projected rotational velocity, so the Vigan I. But most importantly, one of the important goals of this survey is to measure the molecular abundances of the atmospheres of these targets, so that it allows us to have a better understanding of the formation mechanism of these companions. All right, so after observing a target, the first step we do is to have a simple detection confirmation. This method is done using a technique that is similar to what was done in Rufio et al. 2019 or Landman et al. 2023, where we're using a forward modeling of the signal to see what we have in our data set. So basically, we are simply estimating the stellar contamination in our data and the planetary contribution, which is multiplied by the response of the instrument. So once we are doing this modeling of the signal using this forward modeling, this is the type of result we can see. So we have, here I'm presenting you some of the results from the brown dwarf we have been observing. So the ones that are relatively easy because they are quite bright is brown dwarf. They are hotter, easier to observe. And so here I'm presenting you HD 4747b, HD 112863b, HR 3549b. And for these 3 brown dwarf, you can see that you have a nice detection peak. So showing again that HiRISE is working as expected, with an SNR of this peak between 10 to 20. So a clear signal that we have retrieved correctly this target, that the observation went well. But now HiRISE isn't only working for brown dwarf, it also works for exoplanets. While they are obviously dimmer, so it's a bit harder to characterize, we still had a nice detection for beta Pictoris C. So we could, after observing beta Pictoris C and after doing this forward modeling I talked about, we could see the nice CCF detection peak. We also had a nice detection for 51 Eris b, which is also a famous, well-known exoplanet, I would say. And finally, we had also a detection for AF-Lab b. So we were quite happy for this result for this exoplanet. And especially, I invite you to for the talk on Wednesday by Elisa, who's going to specifically talk about IFLB, how we observe it, and what we did to retrieve this observation, and to how we analyze this target. All right, so we have been able to observe brown dwarf and exoplanets. We were able to confirm the detection. Now we can move to the main and important analysis of our data. For example, here I'm showing you a retrieval analysis using Petit Rattrand in order to better characterize the atmospheres of our target. One of the goals of this retrieval is to get more information on the molecular abundances of our target. For example, to know the CO ratio in the atmospheres, or to know the metallicity of the target. And by doing so, we can know whether we have a cloudy atmosphere or whether it is mostly clear atmospheres for our target. And all this data that we are finding using retrievals can be used in our survey to learn more about the formation mechanism of our companions. All right, so I'm going to end there with a conclusion. So first, HiRISE is a promising instrument. We had a successful commissioning in the summer 2023, and since we have been able to move to our survey, we were able to detect brown dwarf and more difficult and dimmer exoplanets. Obviously, there are still some work to be done in order to characterize the atmospheres of these exoplanets, but we're happy because we have more observation to come, and that's going to help us to pinpoint trends in the formation and evolution of this object. Thank you.
So thanks, Giulia.
Right. Can you hear me? Okay. So, hi everyone. My name is Giulia Roccetti. I'm a second-year PhD student at TISO, and today I will present our work on future application for Earthshine. So let me start with introducing you on Earthshine observation. So what is Earthshine? For us, this is a way to actually observe the Earth as an exoplanet. So what we actually observe is the sunlight, which first gets scattered by Earth atmosphere or by the planetary surface. Then some of these photons might travel on the darker portion of the visible moon and get reflected back on Earth. We're going to collect them with our telescopes. So what we're actually doing is to use the moon as a diffuse mirror, which means we are going to observe the Earthshine spectra as it comes from a single pixel. So we're going to completely lose the spatial information, or where on the atmosphere or on the surface of the Earth these photons got scattered or reflected. So in a way, these observations really resemble the way we can observe the Earth in reflected light. Okay, so why do we do this very complicated thing about Earthshine instead of using, for example, satellite observations to try to characterize the Earth as an exoplanet? I would like to mention that usually satellite observations offer really high spatial resolution observations, so we can measure very precisely some local properties of the planet. But what we are interested in when we do exoplanet observations are mostly disk-integrated properties, so we need our spatially resolved spectra. And the other advantage to observe from the ground with our big telescopes is that we can get for very high spectral resolution observations like we do for exoplanets, while most of satellite observation usually have low spectral resolution instruments. In addition to that, we actually observe Earthshine using polarization. For us, there is a very strategic way, so this is a very strategic way to actually observe Earthshine because we have one problem. For us, our photons are traveling through the Earth atmosphere twice. First time when they get reflected, and a second time during the transmission. It's really hard to disentangle the signal. But using polarization, we do not need to care for the telluric correction because the polarization state of the photons before and after the transmission to the Earth atmosphere is not going to be affected by scattering processes, and thus with polarization we eliminate the telluric correction. In general, we also think that polarization can be a good method to apply to exoplanets because most of FGK type stars are almost completely unpolarized, and thus using polarization we can enhance the contrast between the planet and the star, and in general polarization can offer us more information about the properties of the planet itself. So to summarize, what causes polarization in our exoplanet? We have an atmospheric component, which is due to single scattering processes happening in the atmosphere. So we can have interaction with molecules through Rayleigh scattering or with cloud droplets through following the Mie scattering theory. But we can also have, of course, surface reflection, which can actually polarize our photons. There is one particular feature which I want to mention, which is the ocean glint. It's indicated here is this really bright spot over the ocean on this satellite image of the Earth. And this spot already appears very bright in intensity, but is even stronger and brighter in a sense in polarization. At the same time, we can have other components in our atmosphere which can depolarize photons, which usually happens through multiple scattering processes happening with clouds or aerosols. Okay, so we have a huge catalog of these Earthshine observations got in a 10-year span. And what we can actually do is actually do some simulated images like I'm showing here. This is just a small subsample of our catalog. And you can see exactly the geometry of the date and time on where these observations were taken. You can see that as the sun, earth, moon geometry changes, we can observe different phase angles. So we can go from almost full phase to a very small phase of the Earth in reflected light. And you can see that we have also different features. We can see the Earth over the Pacific Ocean, where it is almost like an ocean planet, or we can have like a mixture of land and ocean surfaces. So we have many of these spectra obtained in low resolution, and what we want to do, of course, is to model them. So we use a Monte Carlo radiated transfer code called MYSTIC, which is optimized to do Earth remote sensing, so it can simulate full 3D realistic atmospheres with patchy clouds and inhomogeneous surfaces. I want to show here which was the state of the art of this modeling of Earthshine. You should focus here on the black line, which are the observations of Earthshine corrected for lunar depolarization, and all the other different colors and lines and dots represent many different models. And you can see that we were still struggling to fully fit these Earthshine observations in polarization. So I need to do a lot of work to actually investigate why and improve our modeling approach. The first thing I need to do was actually improve our planetary surface refraction modeling, because many satellites can tell you very precisely with a very high spatial resolution, which is the albedo, so the reflectivity of the planet, but you don't know which is the albedo between the different spectral bands of the satellite. So what I did was to create, it's not showing, a data set for the hyperspectral albedo maps. So you can see that's changing with the wavelength. I can capture the variability of the albedo of the planet when it gets very bright here, for example, during the vegetation red edge phase. And now going in the near infrared, for example, the planet is going to get very dark at the poles, while in the near infrared also the deserts are going to start to get very bright. So this data set was really crucial to actually fit in a good way the Earthshine spectra we have. At the same time, I need to investigate a lot what was going on with clouds, because of course, the albedo of the planet, when you do reflected light simulations, is going to be strongly affected by cloud properties. And I thought that it's going to be a very easy task to actually inject some cloud models for the Earth coming from, for example, climate simulations and satellite observations, but it was not the case. So you can see in the first image here on the left how like global cloud properties appear from this ERA5 reanalysis. So this is basically a global weather forecast model validated against satellite observations, and you might see it's way too cloudy than it should look like. So what we need to do is actually make the clouds even more patchy to get a more realistic image of the Earth, like in the second part. So we need to develop a cloud generator algorithm, which means we are dividing our like global weather forecast model in subgrids, like in this sketch here. So what we're doing is actually making the clouds even more patchy. What we want to conserve is, of course, the cloud cover and the optical thickness. So we want to conserve the total mass of the clouds, but we want to have like much more realistic reflectivity spectra. So what we found is that these cloud inhomogeneities we're introducing in our model are really fundamental and strongly affect the radiative response of clouds. Okay, so now going back to our like Earthshine observations, I want to show you now how we can fit actually between the model and the observations. So here you can see in polarization we have a very good agreement both in the continuum and in, for example, the oxygen A band, while in intensity I would still say the continuum is more or less okay. Some features are not super good also because, as I mentioned, it's much more complicated to correct for telluric lines in intensity. Okay, so actually, studying the continuum, what we can learn is some variability among different surface features. So for example, here in intensity, you can see that I'm modeling an ocean planet, which for me means like no land component, versus a rocky planet, which is a mixture of land and ocean. And what you might see is that it's really hard to disentangle among the two different models as a function of the phase angle. So these are actually phase curves. You can see there is only a small variation here, but this is actually inside the variability due to clouds. So it means I'm running exactly the same models with many different cloud files to catch also the cloud variability. If I do the same in polarization, the situation gets very different, because until 90 degrees of phase angle, you might see it's still very hard to disentangle among the two different models, while if I go in these if I go in this high phase angle scenario, so between 110 and 150, what you might see is that there is a huge spread between the ocean and the rocky planet, and this spread is much larger than the spread we can see due to the cloud variability. So what it means that this is a really good region actually to observe your exoplanet in polarization to try to actually characterize surface features. So if you get a really strong polarization value in for this phase angle, it might mean that you are detecting an ocean on the surface of your exoplanet. Now, going in high resolution, what can we do? What can we learn about the Earth? So we have validated our model with low resolution Earthshine observations. So we know now that like how our methodology works. And I'm trying to see, for example, how the oxygen B band in the near infrared looks like with a spectral resolution of 100,000. So for example, what HANDAs we'll have for the ELT. So here, for example, you can see the different line forests in the oxygen B band, and how they are affected by clouds, both in intensity and polarization. And even more interesting is, again, trying to say something about the surface feature of the planet observing reflected light. So this is, these are the water band in the Y band, so from basically 920 to 940 nanometers. What you can see here in intensity is that in the cloud-free model, the ocean planet and the rocky planet scenario are basically the same. Of course, they have the same spectral features, but the continuum is kind of shifted a bit lower for the rocky planet. So you might think this is a good signature to try to assess like the surface variability of the planet, but as soon as you had the clouds on top, you might see that this variability disappears because the clouds are gonna completely smear out this kind of feature. But something that was already found by Terese and Stam, where they studied like the lowest resolution spectral lines and how they are affected by polarization, is actually the following. So what you might see here is that, again, having your ocean and rocky planet scenario, the situation is very different. Because for the ocean planet, your continuum in high resolution is gonna be up here, while all your water lines are gonna show up in absorption compared to the continuum. This is a very distinct features because if you look at the rocky planet scenario, in polarization again, your continuum is much lower, is below here, and all your water lines are going to show up in emission. So this is really a distinct way we can try to characterize the surface of an exoplanet, observing this in reflected light with high resolution. Of course, when you're going to add clouds, the situation is going to be a bit more complicated. You still see there is a difference in the continuum here in this region, for example, and the lines are going to behave exactly the same. So the water lines are going to show up in absorptions for an ocean planet surface, while for a rocky planet, so where you have land, the lines of water are going to show up in emission. Well, here the situation gets very complicated because the transmission in intensity is getting very, very low. Okay, so to summarize, we think that Earthshine is a very nice way to try to characterize the Earth as an exoplanet, because we can also observe that at many different phase angles. And we think that this is a very important study to validate our reflected light simulations that we found are very, very sensitive to clouds and surface properties. In particular, we found that polarization is absolutely incredible in distinguishing among ocean and land surfaces, which is something that is really hard to catch in intensity. So this might represent an advantage as an observational strategy, complementary to what we can usually get with total flux intensity. And I'm kind of trying to bridge the gap between what we are doing here with Earthshine to exoplanets. So I'm leading a proposal now to try to characterize an exoplanet in polarization. Thank you very much.
Thanks, Giulia. There are any questions for Giulia? Hi. I hope you enjoy your coffee. And now we have the last speaker of today, a keynote speaker. He is Ehsan Gharib-Nezhad, and he will talk about molecular line opacities. You have 25 minutes. I will tell you when you are at 20. Thanks.
Sure. Thank you. Hello, everyone. My name is Ehsan or Sam Gharib-Nezhad. I'm a research scientist at NASA Ames Research Center. And also, I'm a task lead for Habitable World Observatory, the AI/ML, data processing and analysis. So, first of all, thank you for having me here. It's a pleasure, and it's so exciting to see all of you. I was thinking to talk about, we are in characterization era, not in detection, and talking about these ones to like spice it up a little bit, but you're already excited, so no need to talk about this. Probably I can show you one slide from Elisa that she presented today, and that is something I'm interested, or that's what I do in my daily basis. I look at those question marks, not only on those, but also on the FE, on OH, on other these, and I ask myself, is the line position is correct? What is the reason for that, like question mark? What is if these lines are match or not? And I ask these questions, but you already know all of those, so I don't need to repeat them. But maybe through a little bit like few keywords, like composition, climate, non-equilibrium, like haze, clouds, measurement, lab, ab initio. I mean, those are all words that I directly or indirectly talk in and use in my daily basis. So just wanted to say this is the impact that I see in line list. And well, you already have seen this one. This is transmission, and with transmission, this is the way that it works. And we are all stuck with opacity. Like if line list, if opacity has issue, if it's not complete, if it has like inaccuracy, your results, it has problem. Your characterization, I mean, that's something that we are doing at NASA Ames, and also many teams are working on to create a better line list and better opacity. And also, I mean, with high resolution cross-correlation technique, it's not only detecting and characterizing like one molecule, but also you have isotopologues like 12 carbon versus 13 carbon here in carbon monoxide, in CCF. And also, this is not only that, it's also with James Webb. That's something Ben Liu will talk, I think, in a few days about his work. And yes, this is not high resolution in like HiRISE stuff, but it's very high resolution in white dwarf. And this is something that I think in every day. What I think is that I tell myself, you open like HiTemp, HiTran, and you look at the data and you want to download like water line list or anything. And so yes, you are looking at the range and you want to, I mean, click on the data, maybe you zoom in with the dot par. And my question is that, do you care about what is going on, what is in the header, what is like these lines, these numbers are? If it is boring, unfortunately, that's my job. So line list. Line list is important. When I look at line list, I look at line position. With line position, it comes from the potential energy surface. Look at this spectrum. This is from Hargreaves. This is methane, and it's showing the comparison. Hargreaves, the laboratory, plus the previous one from exomol 10 to 34. And also, you can think about impact of water, like different line lists on HiRISE stuff and on the characterization. And that is my problem. And sometimes I ask like someone, like I have been in conference and I ask this question, what water line list you are using, and people don't know what it is. And I was like, okay, there is difference between them. Like, look at this one. This is Pokazatel versus BT2 versus Schwinky, and you can see line position, there is extra lines, there is like intensity different, and this is all thing that it matters, and you can see on this paper. And also intensity. When we talk about intensity, I mean, this is two examples, one from Xin Zhuang, and this is for CO2, this is recent work, line list, and the other one is from Clara, Sosa Silvia, and they are showing, yes, this is a standard way, they are showing their ab initio work versus laboratory work, and they try to, I mean, there is a lot of information. That's something I'm trying to say. There is a lot of information hidden. But if I go back to, I don't know, quantum mechanics, like PhD, like textbook, etc. I look at a column and I say, okay, this is Boltzmann distribution, and as a result of the light, we have like exciting, and there is like equation, there is Einstein coefficient, which is also a part of what you see inside a line list, and also there is this line profile, and that's also another challenge, because with line profile, we have Doppler, we have Lorentz, we have Voigt, and if you are not having enough of this, also we have many other profiles, line profiles, and those are all matter. When you look at, when you take this opacity, there is many things hidden there, and it's important that we understand the line list. We know what is going on there. And yes, I mean, example is like TIO in WASP-33b. Today I talked a little bit quickly with sorry, I forgot his name. I have jet lag. But anyway, so the question about if there is detection or claim of detection or non-detection of TIO in WASP-33b, a hot Jupiter, this comes from the point that what line list you are using, what opacity you are using. And here you can see they have used CRIRES, they have used Phoenix, they have used other line lists, and they got a different correlation coefficient. And I mean, I was motivated. What I did in my work in 2019, on recent work, it was, I compared like the exomol Toto versus the CRIRES, and this is Toto, the first version. So that's another thing. If you talk to like Laura, my chemist, you can see like she has done like continuous work on TIO to make it better. And there is, I mean, the TIO is going on and on. There are groups saying there is TIO, there's groups saying like there is probably TIO, and it's important that when we talk about the line list, or when we use it in our modeling, we know what is going on, what is behind this line list. Why? Because, for example, someone like Peter Bernath, a lab guy, doing the measurement and compare it, the laboratory, with the theoretical. Here he has used the Toto, and there has been some discrepancies, which, yes, this is laboratory work compared to theoretical. And that is a motivation, because TIO, it's not an easy molecule. And the same for FEH, for VO, for like, with ab initio work, or even with laboratory work, you measure the lab, in the lab, but when you do the measurement, when you do the assignment, those assignments, this is a lot of many electronic states. In some you have multiplicity. There is a lot of like spectroscopy parameters going on there, and you get the end point, which is opacity, what we call opacity. And what we do as well, and this is the different group also have done, what in 2021, I generated a new set of opacities, and also my colleague Aisha here, and it was a part of work with Mike Lyon. We compared the impact, we assessed the impact of different old versus new line lists to see, should we ignore the update of new line lists? And the answer is no, because up to like 8 Kelvin difference we will see in the temperature gradient, the temperature profile. And also, and this is hot Jupiter, a generic hot Jupiter. In the transmission and emission, you can see it's up to 300 in the transmission, 85 ppm to part per million in emission. And to give you an idea of, with James Webb, it's 10, 15. The noise floor is 10, 15. So obviously you can detect these differences. And these differences are, of course, when they are important in James Webb, they are definitely important in your work as well, with the line position and etc. And well, I published this data, but also on that paper, I have a long paper, and on that paper, I have a big table comparing my results with others as well, because it's important. There has been, this is community work, there has been many works done by different people, different resolutions, different temperature, pressure grid, and also I have 2 pages discussing the challenges, which it was basically my daily conversation with my colleague, Richard Friedman, to talk about what is the limitation that we have when we talk, when we work and provide you with the line list. And also going on and on, there is pressure broadening as well, because pressure is important. It impacts, like if you work on a steam atmosphere, like high percentage of water atmosphere, and you use water, but with hydrogen helium, you get up to, I don't know, up to 85 difference. There is a big difference in the error or bias. You bias the characterization and the observables. And also there has been a follow-up work by Elisa Kempton, which is, she has used water with self-broadening opacity, and she generated grid models. And that's also a valuable thing to see, to look at. Another thing that I led over the last year, it was assessing the impact of wing cutoff. And this wing cutoff, this is when we calculate, like, I mean, think about one line list, it is, I don't know, like VO, the new one is 59 billion, I think. Each line by line, we have to cut it at some point. It's void profile, and that has an impact. Like if we say, let's cut, have the wing cutoff in like 10 micron versus 10 wave number versus 100 wave number, you see the impact, the difference. And the difference, if I show you in a colorful plot, in a heat plot, the temperature versus the pressure, the absolute mean error, it's up to 100% difference. And we published this in RASTI, and we discussed like what is the standard way. And this work is HiTran. It has like team with like Yuli and Rob, and also it's people from ExoMol, and it's from NASA Ames, and also we had Cornell. And there is a dagger here. I know your question is, what is this dagger for? In this paper, if you look at this dagger, it says all authors have contributed equally, and I made sure to have this. And what my point is, pressure broadening, I mean, line list is a community work. It's not a work of one person. We work all together, and especially on this, there is different expertise came together about line mixing and etc. So enough about the challenges. Now I want to say what our contribution as a part of my contribution and our contribution at NASA Ames. We think about database, lab measurement, ab initio, theoretical calculation, tools and pipelines, and also radiative transfer modeling. And well, if I talk about the database that we are working in, and my colleague, Dr. Natasha Batalha, is leading at NASA Ames, and also the team member, it is from ExoMol, from different institutions that you can check. There are a few words that we believe on. We believe we are trying to make it complete, accurate, available, transparent, and a standard. Like we provide a standard about like what is wind cutoff, discussing what is the warning, what things we should care about. There is a lot of information there. And there has been like different phases, phase 1 and 2, which is building the data having like hosting the data at NASA, and also providing an interactive database, this platform. This is something that has been done. Now we are in opacity phase, which we are computing data. And with the computation of the data, it's not only my data or one single person data. What we are instead trying to do, we want to, I mean, this is an example of the interactive platform. What we are doing, we are asking for data from different teams. So if you email us, we answer you with an open arm and say, hey, yes, please, if you have data, if you need information, if you need this data, this is something that we are providing to the community. And we are thinking, we have experts at high resolution, low resolution, on emission, transmission, I mean, everything. So this is something that we are doing. It's not only generating, that's not our work. What we are doing science, not generating only opacities. We look at pressure broadening, etc. And that is another thing I want to talk about, lab measurements. So I had the pleasure to get, I mean, over the past 3-4 years, I raised more than $1.6 million. And that money, it was from XRP, 2 XRPs, one on theoretical generating opacities for high metallicity. The other one is doing laboratory measurement. And here also I want to talk about laboratory measurement. So a little bit about here, one picture with my colleague. So this work is a co-lead with my colleague from astrophysics lab at NASA Ames, Salma Bijoui and me. And also it has Natasha Batalha, Farid Salama, Yuli Gordon, and also you see our interns. And the idea is that we, in the detection, like in cycle 1 of James Webb, we are going to see many detection of high metallicity atmospheres. Super Earth, sub-Neptunes, and over there you don't expect hydrogen dominant. Mostly you expect to see like high percentage of water, of CO2, of other molecules. And this is our concern. This is what we are doing. We are asking ourselves, okay, in the theoretical side, we are doing measurement, calculation to calculate pressure broadening, but on the laboratory side, we are using, and my colleague is, she is using a laboratory setup, laser setup, to do the measurement at high temperature. And so what you see here on the right side, this is single path. On the left side, this is multi-path, and that's why you see 15 meters, because you have like a small cell, gas cell, but this is multi-path, which in total you get 15 meters. And the temperature that we are interested in, at this point is 300 to 600 Kelvin and up to 1500 Torr, which, okay, you are not lab people, so so 15. So this is in Torr, but it's about like it's about 2 atmospheres. So I mean there is a lot of details going on there, but the important thing is that we also trying to provide laboratory measurements, and that's a part of it. The other part is that I'm leading this package, which we will disclose the name and and make it open source soon, but it is spectral analysis, and it has different components. I don't have time to go to the details unless you have questions, but just to showcase, it's basically this is laboratory measurement, just preliminary data of methane, and here zoom in, and this is the way that we extract the spectroscopic parameters. And those spectroscopic parameters, those parameters are line position, intensity, and also the void profile and other profiles, depending on our signal to noise and etc. And with Maestro, so the database that my colleague Natasha Betalia is leading, and I'm also working leading the opacity part of it, it benefits different things. It helps us to understand chemical models. It's for chemical climate models like GCM and stuff. It's also for clouds, which we have Virga for it. And also, recently it has been like a year and a half, which I'm leading the AI/ML part. And also, so this is an example. And it's gonna be a little bit in rush, but I'm just throwing it, and later we can talk more if you are interested. So this is an example. What we did, we used a deep neural network, and this is a work that it was in collaboration inside NASA Ames, but between two different codes. It's code S and code T, which is between aviation and science. And we had different, in team, we have different people. And example is we trained the model. Usually people use forward or retrieval modeling. What we did, we trained the neural network on the synthetic data. It was from Bobcat, if you are familiar with those, and Sonora Bobcat. And we predict the results for this object. This object is good because it's well studied, and also we showed the temperature, the log G, the C/O ratio, and the metallicity. And there's distribution, which it comes from the uncertainty because of the radius, because there is different things going on there, and I'll talk later. But we also compared our results with the previous results. For example, with my client 2017, you can see ours is the star, the log G and the T. And we also compared our results with Zhang et al. And so, sorry. And so you can see, there is also other work, like there has been done work on using traditional models, random forest. But also what we did, we developed a package. It's called Telescope ML. Which is open source, that if you would like to contribute also, that's something I would love to see if people, and I have actually a colleague in Germany that is adding XAI, explainable AI, to explain to explain what is going on inside deep neural network, to choose a specific feature. Anyway, so what I want, this is my conclusion, and I have 1 minute, so I can talk. So it's a little bit hard. I throw many topics here, and I don't know really how many people or other people are also going to talk about line lists today in this workshop. But what I want to say is that if you leave this room and have this question in your mind, what if you have been using the first version of water line list? I don't know, BT2 or whatever, like the first one. Or what if you ignore the pressure broadening and like self-broadening of water, and just think about hydrogen and helium, because, I don't know, you're busy or whatever, you don't have time to incorporate it in your model. Or what if, like, wind cutoff, I mean, if you change the wind cutoff from 100 to 1 wave number, the computation of opacity data get too much faster. It's a lot faster. If you don't have time in computing your opacity and just like you want to quickly do the calculation, I mean, what will happen? If you leave this room and you ask yourself these questions, to me, mission is done. I will achieve my goals here. Other than that, we would love to hear your input. If you have any question, or if there is a molecule FEH, for example, in the morning, someone asked. These are all, I mean, this is great. I had, for example, experience talking to Caroline Morley about a data set, about opacity that we provided them, and they help us to understand like a part of it. There was like an issue, and that's also very valuable. Like your feedback, everything is important. Besides, if you are also interested in HWO mission, Habitable Worlds Observatory, also I'm a part of that. I would be happy to connect you to someone, or if you have questions, if I can, I would love to answer. Thank you so much.
No, maybe you raised the